Good afternoon and welcome to this day number 2 of this workshop on P4 programmable switches. My name is Jorge Cuchigno from the University of South Carolina, one of the organizers of this workshop. First, before we start, I just want to point out that all the material from day number 1 is already online in the website that we have for the workshop. That is here online. So this was day number 1 a week ago, and we have the recording plus all the set of slides that we used back then. For day number 2, also the material is already online, and we'll be posting the video early by tomorrow. Again, this is day number 2. I want to welcome you all. Thank you for coming. I want to let Mariam Kiran, another co-organizer of this workshop, if Mariam is there, you want to briefly talk about the workshop, Mariam?
Yes, hi everyone. So this is Mariam. So I'm joining from Oak Ridge National Lab, which is in Oak Ridge, Tennessee. So this is the second time I've been trying to do this workshop with Jorge. So I used to attend this workshop, and then I started organizing it with him. It's a great workshop to learn how to use P4, and some of the students have come up with some very interesting examples on how they've started using the P4 data for their networking work. So great to have you all here and learning from you as well. Thank you.
Thank you, Mariam. And this is day number 2. Before we go into the detail, I would just spend the next 2 minutes talking about the workshop. So as Mariam said, it's about P4 and additional topics. Today we'll talk about Science DMC, and then Neil Carwell, the main author of BBR Congestion Control, will be talking about updates, BBR version 3, and then some P4 applications that are related to queues, buffers, monitoring. There is a relation between the first 2 presentations, Science DMC and Congestion Control, and then related to P4. So hopefully this will be of interest from you. So this is the agenda. We will have a talk on Science DMC, important issues such as congestion control and buffer sizing, then more about congestion control. And then we will have 2 hands-on sessions, how to monitor buffer occupancy with P4, and then how to calculate packet interarrival times with P4 switches. The main difference between P4 switches and legacy switches is that we will experience the very high resolution, granularity, fine-grained measurements that we can produce with P4. So that's the program for today. I want to remind you, if you're interested in using all the material that or any of the material that we create here at USC, feel free to email us and we will give you access. So these are some of the virtual lab libraries. One library is equivalent to about between 10 to 15 virtual labs that we typically use in classes or workshops or self-paced learning. With that, I will go to the agenda, and I want to make sure that Doug Southworth, I just want to confirm that you are there.
I am here.
Great, thank you, Doug. Let me briefly introduce the audience to you. Doug Southworth is an engineer scientist at the Texas Advanced Computer Center. He's the lead developer for the NetSage flow monitoring project, and is actively involved with Personar in both deployment and training roles. He also works with the Engagement and Performance Operations Center to troubleshoot complex network issues and offer network design assistance. Before working at TAC, Southworth worked for international networks at Indiana University, doing proactive network performance analysis and working with partners to improve transfer speed and scientific outcomes. Thank you very much, Doug, and I will let you share the screen right now.
All right, thank you much. So yeah, we're going to start off today talking a little bit about basically Science DMZ and some network design considerations. So as we delve deeper into kind of congestion control and P4 programmable switches and stuff like that further on in this workshop, we've kind of got some of the design basics and goals of what we're doing under our belt to start with. Let's see. Well, it's not letting me advance my slides. Give me 1 second here. I'm going to drop my share and see if I can get this to behave. Okay, let's try that again. Well, interestingly, it's letting me move forward and not backward. 1 second, let me see what's going on here. Oh, geez, it's being really fussy. Ah, okay, got it. All right, third time's the charm. There we go. So, when we're talking about using networks on campus, commonly we talk about building out our cyber infrastructure, and there's more than one method to doing this. One size of network, one style of networking approach doesn't work for everything. What works well in the commercial world may not work well in the research and education world. So some of the stuff that we're trying to consider is, does it work as expected right now, or can improvements be made? And if we do make those changes, is that going to satisfy only one group? Is that going to satisfy everyone? That's the ultimate goal, is to make sure that everybody's happy and not just make a change that satisfies one specific group and upsets another group. We want to make sure that we've designed this so that everybody that has a hand in it is happy with the outcome. And how do you know when you're done with it is another interesting question. Do you have metrics before and after that show improvement? And is that improvement enough? Can you do more? You're going to be driven by kind of the numbers and the outcome of that moving forward. So there's a lot of different considerations. And so we don't want to just build something out because we have a pile of money and we're told to build a network. We want to be very purposeful in our design and in the ways that we approach this. So one of the things we do is we look at network as part of the instrument as opposed to just purely infrastructure. So whether you have a massive particle accelerator or a relatively modest, device that's just used for genomics or something along those lines, or somewhere in between that scale, we look at the network in R&E as an extension of that instrument that is already there, that brings the data from that instrument to any researcher that may need it. So it's a little bit of a different mindset than purely just building a network for the sake of building a network. So what we're interested in is usability. We're not just looking at connectivity. Connectivity is just the point, the start of what we're looking at here. It's not the end point. So really what we need to do is understand the space that we're building in. So when we look at our network architecture, again, we're not looking at it as a network. We're looking at it as a holistic solution. So we need a data architecture. We've got to be able to look at the data that's produced in R&E and look at its entire life cycle. We're not just interested in hooking up a network and saying, hey, we've got data from A to B, so we're done. What does the entire life cycle of that look like, from the time it's created to the time it's used, to the time it's analyzed, to the time that it has to be curated? We want to look at the life cycle of the data even after the experiment is done. What happens with that data? Where is it going to live beyond its initial usefulness? Because people often come back to that data for experiments down the road or to reference it. So we're looking again at this kind of as a holistic thing, as opposed to just creating a network that moves data. So most of the stuff that we're doing right now is still TCP. That's going to be the default kind of engine that drives the internet right now. Even with some of the other things we're going to be talking about today, TCP is still very prolific. A lot of times we've got these converged network architectures where it's designed to handle research traffic and commodity traffic and inter-campus traffic, and all these things are combined onto one network traditionally. And there's still a lot of legacy transfer tools out there, SCP, FTP, different scenarios like that, where even though there are parallel stream, high performance network protocols out there, we still see a lot of the legacy ones out there. And also sometimes networks, we only tend to see the hard failures, right? We get the trouble tickets when something is completely broken, but a lot of times we don't see concerns come up in a trouble ticket type of system where it's connected, but it's just not very fast. And so if we're waiting for those kind of tickets to show up where people think maybe the performance isn't adequate, we may be waiting a long time, or we may never see that. So there's a lot of hurdles to fast and efficient TCP transfers and research and education transfers, just because of the way networks are typically built and the way that our reporting typically works. So again, TCP is still the engine that's driving almost everything out there. ESNet says that 95% of their traffic is still TCP, and that's as of 2023. That's now. So TCP is very, very timid. As soon as it sees packet loss, it thinks there's congestion and it backs off. And there's very good reasons for that. If you look at the way it was designed initially, it had to function that way. And even in a modern network, that's actually not a bad behavior, but you have to understand that that is the default behavior, that it's going to back off, it's going to be very timid. And so when we look at our networks, we need to design them so that they are open and free-flowing as possible to eliminate packet loss as much as is absolutely possible, so that we can get that high speed, high performance. And when you look at networks, typically we're looking at the local network, and that's what a lot of even ISPs in a local, or small region are concerned with. So they're not really concerned about a small amount of packet loss, because over a short distance, small amounts of packet loss, or even relatively large amounts, don't affect throughput all that greatly. But once you get out of your kind of local area, you get into the regional area where you're 10, 15, 20 milliseconds out, an incredibly small amount of packet loss, in this case, we're talking about 0.0046%, has an incredibly detrimental effect on throughput. We're down to a gig, basically, once we're out of that 12, 13 millisecond, down from 10 gigs. And the situation only gets worse as you cross continents and oceans. So unlike a traditional commodity network, which can cope with local small amounts of packet loss, what we're demanding from R&E networks is almost nothing less than perfection. We need this to work, and we need it to work relatively flawlessly to do what we need it to do for large transfers. So the Science DMZ is really a performance-based approach. It's a set of principles. There's no one specific, this is what you do to build a Science DMZ. You incorporate a whole series of principles and then design a network based on those principles that works for your science and research, education, data movement goals. And so some of those are what we've got listed here. We're looking for well-configured data transfer hosts. We need capable network devices. We need a high-performance data path. And we need to know up front that what we've done works. We can't just build a network and say, well, we followed this design path, so we're sure it's going to work for that data case. We actually need to have regular testing and kind of a proactive troubleshooting mindset of, we're going to prove the network works. So that way, when a researcher is using it, they know what to expect. And if they're not getting what they expect, then we can take a look at why. But we already know that the network up front is doing what we designed it to do. So the Science DMZ is basically a friction-free network path. We take out we basically try and push the devices close to the edge of the border as possible, so that we're not going through switch after switch after switch, hop after hop after hop, getting deeper and deeper into the network. We're only using devices that are capable of doing those long distance transfers. So we're looking for store and forward deep buffered switches. We're not looking at cut through style switches that don't have enough buffer to support our transfer. Everything is optimized around the distance of the transfer that we're planning on doing on a regular basis, the type of data transfer, and the amount of, the data size that we're looking at. So, and again, we're going to have that per sonar node in there, or we're going to have some sort of tool that allows us to do proactive troubleshooting, proactive performance analysis. And so these principles here are the guiding design behind what we're doing with the Science DMZ. And so Jason loves to throw this slide in there. I lifted this from him, where we can design whatever we want, but the user experience is going to be different than what we design unless we work closely with that user to tailor that experience. So we're gonna, again, as I said earlier, the Science DMZ can take a lot of different forms, depending on what our goals are, depending on how far away the transfers are in terms of milliseconds. Are we talking a 50 millisecond RTT? Are we talking a 150 millisecond RTT? Are we going from DTN to DTN, or are we going from an instrument to a DTN? Basically everything we're doing, though, centers around looking at ways to eliminate sources of packet loss. We're looking to create the lowest friction network that we can to get as much data moved as quickly as possible. And so what we need to do, and what doesn't happen a fair amount of the time, is to plan ahead for this. So a lot of times the model that we see is a researcher says that they need a DTN. So they go ahead and purchase a DTN, or they ask their cyber infrastructure folks to go ahead and purchase a DTN for them, and they want that equipment close to wherever they are on campus in their lab. And so their lab is logically in the network several hops away from the border, and it works, right? You can put this in your lab, you can fire it up, you give it an IP address, and it's technically connected to the internet, and people can reach it and do transfers. But the performance part of it is where things fall apart a little bit with this kind of model. So if we have per sonar at the border, then we can at least start to say, well, we know the performance at the edge of the network is good, and we can start working our way back inwards to find out where the problems are. But this is where kind of being proactive about the planning stage up front can help eliminate some of these hurdles. So again, this is kind of that model of an ad hoc DTN deployment, right? You've got this data transfer node on the bottom left there that is buried way deep inside the network, and it's just connected to what is effectively a network designed for commodity and commercial traffic. And this kind of path rarely results in adequate performance. So when we're looking at a Science DMZ, we're going to take a different approach. We're going to have our high performance DTN as part basically connected to a Science DMZ switch, and that switch is going to have access directly to the border router and then out to the WAN. So we have one hop or two hops at most through equipment that we have specified and purchased specifically for this task. And that leaves the enterprise and all the other network associated with the enterprise off on their separate leg where they've always, have been. So basically, we're not trying to make the enterprise network do the work of the Science DMZ. This is a shortcut path to get data out to the WAN as quickly and cleanly and as efficiently as possible. And so we've got several different ways we can do that. We've got multiple DTNs. One of the ways we can do that is employing dark fiber. So we can have DTNs in different places, but if we can use dark fiber to bypass the traditional network and get right to the border, that's a possibility, one way we could do that. And so part of the reason for this, part of the reason we're trying to bypass that core part of the network is we need different equipment. We need stuff that won't work that works well in a traditional network, won't work well for us in a DMZ. And part of that is because if you're only dealing with a few milliseconds of latency, the switches that can cope with that, the routers that can cope with that, are relatively inexpensive. When you start looking at the type of equipment that will allow you to cope with 100 milliseconds of RTT or 200 milliseconds, those are drastically more expensive. But on the box, they look the same, right? This switch does 10 gigabit. That switch does 10 gigabit, but this one costs, 5, 6, 8 times as much as that other one. We're just going to go with the cheaper one because it has roughly the same specs. So part of what we're dealing with is packet burstiness, and we're going to talk about several concepts here. But one of the things we're going to look at is what this means in terms of buying equipment that's going to work for our network. So we're interested in things that a lot of networks don't have to concern themselves with, including microbursts, where you've got these little tiny microsecond timescale bursts of data that can overwhelm a small switch buffer. And so if you look at it, you can say, well, the average flow rate of this is relatively low. It's well within what this switch should be able to handle. And yet the performance is still absolutely terrible. Well, we got to understand what we're talking about in terms of packet rate and error rate on a very, very small time scale. And if the switch is overwhelmed, if it has to queue those packets, it's going to do that right up until it runs out of buffer. And once it runs out of buffer, it's going to drop those packets. So that's part of what we're trying to look at when we're choosing equipment. And so your basic switch architecture is going to be something that's called a cut-through switch. Like a lot of the switches you're going to see on your campus at the top of a data rack are called a cut-through switch. They have very, very small buffers, usually less than a megabyte. And they're designed to take a packet and sling it through the switch as fast as they can, because in a data center or a campus environment, you're usually more worried about latency than anything else. And you don't need a lot of buffer. The packet's going to be where it's going in under 2 milliseconds. So what we're interested in is data coming in from those multiple sources, and then we end up into the buffer section we talked about. So I'm not going to go over every step in this slide, but this is kind of the basic in and out of a switch or a router. So again, what we're considered through, or what we're concerned with, is whether the architecture of this switch or this buffer is a store and forward type of device that has really deep buffers, or whether it's just a cut-through device. And the cut-through devices are not going to work for the type of network that we're trying to build. So how much buffer do you need? Well, the answer is it depends, like everything. But some quick math says that if you're trying to go from New York to California and you want a 10 gig path, a 10 gig capable path, you're going to need 125 megabytes worth of buffer on each connection port. So if you're connecting one 10 gig setup, you need that port has to have 125 megabyte of buffer available to it. And it scales exactly like you want, or like you would think. If you're thinking about a 100 gigabit, that number balloons up to 1,250 megabytes. So you need over a gigabyte of buffer to cope with potential congestion and packet loss. Because again, if it can't buffer those packets over long distances like that, it's going to start dropping them and your performance is going to suffer. And this needs to happen at every hop along the architecture. So that's why we're trying to use the dark fiber to get to the border router and bypass all the internal switchgear if at all possible, because it's prohibitively expensive to put these really deep buffered devices at every hop in your network. So if you can logically get your DTN or whatever transfer device you're using, if you can logically in your network get it directly to the final switch and then the hop out of your network, you only have to have the really expensive gear at your border. You don't have to have it at every hop along your network. And some of those things are out of your control. You don't know exactly what your backbone provider has and those sorts of things. But as long as it's whatever's within your control, we need to design it to cope with these kind of potential congestion problems. So again, just a little bit about buffering. We've talked about this already. Effectively, if you don't have adequate buffer along each spot in the network, your performance will suffer. So in the middle of it, if you only have a switch that has 10 megs of buffer and you've calculated out you need 150 megs of buffer for your transfer, the whole network's going to behave like you have 10 meg buffer. So this is not an issue of looking at each network segment and saying, they're all fine until they get to this point, and then this one little piece right here isn't up to spec, but that's probably fine because the rest of it is. The network functions as a complete end-to-end connection, and if you don't have adequate equipment, if the design is faulty at anywhere along there, you're going to end up with a basically substandard performance. So when we look at this is a 50 millisecond simulated round trip congestion control, a lot of the numbers we see when we're looking at through point is, you know, if you draw a flat line across here, it looks like they're getting roughly 1 gig, maybe, you know, a little bit less than that, 1 gig per second. But this is what it actually looks like during the transfer. A lot of times we only see instantaneous data rate that may be higher or lower. And when we have our numbers after the fact, when we have our monitoring numbers, they typically look at the entire flow and they say, well, the entire flow took this long, so we're going to average that out and say that transfer, you got 788 megabit or whatever the number is. But in reality, it's a issue of this transfer is changing speeds constantly throughout there. And sometimes that's because of, pardon me. Sometimes that's because of microbursts and other things like that. Sometimes it's because of congestion in the network that's causing packets to come back. But wherever you end up having those retransmits, you can see your performance takes a hit. Every time you do that, TCP gets a little more timid and it backs off. So here we have 15 retransmits. All of a sudden the bandwidth backs up, slowly climbs again. We have retransmits here. The bandwidth drops. It slowly starts climbing again. You have retransmits here. That pattern continues over and over and over, and that affects your overall bandwidth during the life cycle of a transfer. So what we're trying to do is eliminate as many retransmits as we can by having adequate equipment in place. Never going to be perfect, but we're trying to fix the problems that we obviously can fix. And so we need to measure and monitor our networks because they're not static. Just because you set a network up a specific way does not mean that that network will function that way 6 months, a year, or 2 years from now. Things that are outside of your control are the networks beyond your campus. So your provider made a change, or the campus on the other end of the connection that your researcher is talking to, they've made network reconfigurations. Or you've got an optic that's failing, or you know, somebody stepped on a cable in a data center and didn't realize it, and now performance is suffering. There's also bugs that happen, and maybe a firmware bug in a router or something along those lines. We need to know all of these things and be proactive about knowing them so that we can keep the network running at a clean, efficient, fast pace. So we talked a little bit about this earlier, and I'm going to hit it again. We're going to talk about soft failures. The hard failures are the easy ones to find because there's no connectivity. That port is down. That link is down. That's not going to work because there's no connectivity whatsoever. I can't ping the device on the other end. Her sonar is the tool that gives us eyes to see in the network where the bottlenecks are, why performance isn't there. So you'll notice that every diagram we have, there's little personar nodes hanging off to the sides of all these devices. It's because we need eyes on the network to be able to find and fix these problems. That means we need to be able to simulate large data transfers. We need to have devices out there that we can run trace routes and trace paths between so that we can understand routing and if there are MTU mismatches or something along those lines. And Personar gives us that visibility into the network to understand the performance of the network and not just the connectivities. So one of the other things that we need to consider when we're building a network for research and education is the data mobility part of it. And so the basic idea, at least initially, was we put these DTNs in the Science DMZ because now the data is not two-part, right? The data is not living on a researcher's computer. More people have access to it if it's on the DTN than if it's living on a researcher's computer. And it also, you know, gives you some manner of security, because if it's on a researcher's computer and they're connected to a typical, commodity style network, people may not have access to that data because it has to go through a firewall, and the security staff on campus may not want people to have access to that machine. So when we do the Science DMZ, we've got our DTN living in the DMZ, and effectively we know who's in the playground. That's one of the that's the way I like to explain the concept of, it's not the Wild West. It's not that there's no security in a Science DMZ. It's that it's extremely limited in scope. We know who is living in the network because we have common sense ACLs at this switch right here that say, you know what, we're only dealing with these particular ASNs or these particular subnets. So those are the only ones that are going to be allowed onto this network in the first place. And so then you have in this particular example, these DTNs right here are Ethernet in the front and then another Ethernet out the back, but they don't have any storage themselves. They are just passing information between this section of the network and this segment back here that goes to a shared file system. And right here is where you have your security controls. Up here at the switch, you've got your ACLs. Down here, you're using something like Globus, where these DTNs, there's no shell access to them whatsoever. There's only Globus, and Globus is enforcing who has rights to do transfers in and out of these boxes. So that's the knowing who's in the playground section of this. And that's part of what gives you your security, is you don't have unknown actors in this zone, and you're not using this Science DMZ zone for printing. You're not using it for web surfing. You're not using it for laptops. You're not using it for anything that you would normally do on a commodity network. This is not happening here. This is solely for the transfer of science data, and its application set is limited to just what is absolutely necessary to make that happen. So using that right tool, we talked about Globus there for a second. Using the right tool is very, very important. So we've got some test data here, fairly recent. I can't remember when this was done, but it was in the last couple of years. But you can see that using SCP versus grid FTP, there's a notable improvement there. In fact, it's almost 24 times slower using SCP than grid FTP. And then once you start multiplying streams, you can get even faster than that. In fact, in this particular test, this is as fast as the hard drives would move in the machine. The network was actually capable of more. So the right network tool, the right transfer tool, actually makes a huge difference in your performance. So it's hard to get all these pieces right. And that's what we're trying to do, is we're trying to design this so that up front we get all of the pieces of the Science DMZ correct. And we test that, and we push it, and we prove it, and we know that we are capable of certain speeds of data transfers because we've proven it all out. And then that way we have a common set of numbers that we can work with the researchers on and say, look, we know that it's capable of this kind of performance. Let's make sure that you're getting that performance when you're doing your transfers with outside operators. So brief talk about security here. We touched on this a little bit, but effectively what we're doing is we're segmenting off the network for security, right? We're not printing, we're not doing web browsing, we're not sending emails, we're not using a scanner. There's not a Windows XP machine that hasn't been patched in 20 years sitting on this network segment. It is only the devices that are strictly necessary for transferring this data to and from whatever location that you need to get data moved to. And so it makes it a lot easier to secure because you only have a couple applications to keep an eye on. It makes it a ton easier to look at performance. And it also makes it easier to troubleshoot. If there's only one or two things that can break, it makes it a lot easier to find what's broken versus a traditional network where there's a lot of moving pieces, and it gets significantly harder to understand where something went wrong. So for putting this all together, what we need is collaboration. We need to make sure that the security people are on board. We need to make sure that the all of the stakeholders, including the researchers, the people making the financial decisions, other staff, other CI people that need to be involved, we want to make sure that everybody understands how the Science DMZ is designed, what it's supposed to do, how it's going to achieve security doing that, what kind of performance is to be expected, and ultimately how it's going to benefit that science. So we need to have an all-inclusive answer that keeps everybody on campus happy. And part of that reason is technical. And part of that reason is political, because we want to make sure that everybody that's involved with it understands how it works so that they don't become a roadblock to progress in this area. If you try to bypass somebody in the network design phase, maybe one of the cyber infrastructure designers, or maybe one of the security people on the network, if you try and do an end run around them because you think they won't help you, they'll become a major roadblock as opposed to an asset. So we want to make sure that everybody is involved and everyone is very clear about what's happening when you stand up a science DNZ. And so there's a lot of data out, or there's a lot of useful resources out there, and ESNet on their faster data site has already taken care of a lot of this for you in terms of defining your access methods and your acceptable use policy and your measurement and monitoring. There's a wealth of data on the faster data site in terms of how would I shape this? How would I build this? How do I talk to people about this? What does a good AUP look like, or at least a starter one that I can modify? These kind of links right here, there's a wealth of information there. And the goal, again, is to be completely transparent. We're not hiding anything. We just need everyone's involvement to make this successful. So that's pretty much it. When we put it all together, we're knowing the users and the use cases. We're letting the science drive our data architecture. We're letting the science push all this forward. We need to understand what that science is, how much data they're trying to transfer, what the life cycle of that science looks like. And from there, then we start building out our data architecture that supports everything from cradle to grave. That includes all the network gear, all the storage, and looking down the road, how that's going to be scalable as that research grows. Their data needs are likely going to grow. So how is that scalable during the 5-year life cycle of the project, or however long it is? And then after that, how are we going to store that data for them long term? So we want to have an answer for as much as we can when we start designing, not just the immediate use case, but what it looks like down the road in the entire life cycle of that science. So that's all I've got for you today. And I don't know if I'll relinquish my share here. And if anybody's got any questions, I'm happy to answer.
Thank you, Doug. I think there are a few messages here. I will read the first one. The SCP performance is due to buffer limitations in OpenSSH. I don't know if you have any comment about that.
I mean, yeah, there is performance limitations there. There's things you can do to get around it, but we're also looking at, if you fire up something like Grid FTP or Globus, it works out of the box as long as there's enough storage infrastructure and network infrastructure to support it. You're really limited by the network speeds and or the disk speeds without any real tuning or tweaking. And so when we're building this, we're building it for access or we're building it for a researcher or for somebody that doesn't have in-depth technical knowledge to be able to use it and get performance as soon as they start using it. And so I've seen people do some pretty amazing things with Netcat, doing block level transfer of huge amounts of data at really high speeds, but they're very technically proficient people. We're building this so that if you use commonly available tools that help us enforce security, that it'll work kind of out of the box without any basically technical intervention from a high level person.
There's a second comment. We'll go through that. Since this is a P4 workshop, what are some switch routers that are, number one, P4 programmable, number two, have sufficient buffer for 100 or 400 gigabit Ethernet science DMC? P4 programmable appears to be the missing piece. I don't know if you have any comment about that.
I'll be perfectly honest, off the top of my head, I'm not aware of any equipment out there that matches those specifications. I'm not saying it doesn't exist. I just don't know off the top of my head of anything that is P4 programmable and has that kind of buffer depth. That's not something that, at least yet, I've had to deal with at the institutional level. P4 is, becoming more popular, and we're learning more and more about it. But traditionally, people are just buying, what the Cisco or Arista or whatever gear they're buying, and buying enough buffer for it. So I don't have an answer for that off the top of my head, unfortunately.
Eli, do you want to add on that? You have been working on buffer sizing. Eli Kafuri is a professor here at USC.
Yes, so for these P4 switches, we've been using here at USC the Intel Tofino ASIC. It's the programmable chip provided with the H-core switches. Now with these switches, the buffer size is very small, so it's different from what's required for a science DMC. There are other programmable switches, but they also have small buffers. I don't think at this point there's a programmable switch that has a large buffer, but what you can do in this case, what we do here at USC, we deployed these P4 switches passively, just for experimentation and measurements. We're going to see later on, because they are very good for monitoring things like the buffer occupancy, which cannot be done very efficiently on a non-programmable switch or router. So what we do is we deploy it passively, and then we get copy of the traffic to that switch, and then we do the in-network processing in there. So this allows us basically to get more visibility and see what's happening inside the buffer. But if you want to deploy it actively inline, at this point, I don't believe that there is any P4 switch that has a large buffer.
Thank you, Eli. Christopher, by the way, HPN SSH overcomes that issue. May I make a comment? Christopher, feel free to make a comment and unmute yourself if you want.
All right.
Yeah.
So my name's Chris Rapier. The issue. So I absolutely agree with you about giving users the easiest tools possible to use in their circumstances, and that's one of the things that I very strongly agree with, because I dealt a lot with trying to support users. We developed a tool called HPN SSH, which actually overcomes the internal limitations of SSH. And it works in the same way that SSH does. And the interesting thing about it is that if you have HPN SSH running as a server, all of your SSH clients, regardless of the implementation, see significant performance improvement, usually between 1 to 2 orders of magnitude increase in throughput. So I just wanted to throw that out there as something to be aware of.
I am 100% going to look into that. Thank you. I appreciate that.
Yeah, just Google HPN SSH or ask me questions, because I wrote it.
Okay. Good to go to the source. Thank you.
Thank you, Christopher.
Yep.
I don't see any other questions. Well, thank you again, Doug. That was very good presentation. And the slides, by the way, are already online, and also the recording will be online probably tomorrow morning. Okay, so the next, we have another presentation before the hands-on activities. We have a guest from Google. Neil Carwell is a senior staff member, software engineer in Google NYC office. He entered the UC Berkeley PhD program in 1996, and then followed his advisor, Tom Anderson, to the University of Washington, where he completed a Master of Science in 1999 with research in the area of TCP congestion control. He worked at Steve McCain's Fast Forward Networks from 1999 to 2002, He has worked at Google since 2002 on projects including GFE, Googlebot, routing performance, the open source packet drill network, stack testing tool, and Linux TCP congestion control and loss recovery. He's currently a member of the congestion control team at Google, and his recent focus has been BBR congestion control. So Neil Carroll will be talking about BBR, the updates, and I believe BBR version 3. Welcome, Neil, and I will let you share your screens right now.
Thank you very much. Yeah, let me, I'm going to stop the video of my head because it's probably less interesting, and then let me share the slides here. All right. Let's see. Are you guys able to see my slides?
Yes.
Okay. Okay, interesting. Yeah, because it's not. Oh, I see. There's the indicator. Okay, I guess Zoom has changed the UI recently, maybe. All right, so thank you very much for inviting me here to give a quick talk on BBR congestion control. I'm going to be talking about both the fundamentals of the algorithm and the history of why we developed it and how it's evolved over time in order to make improvements as we've gained experience with the algorithm. And feel free to jump in with questions as we go. Although if there are too many questions, we might have to try to move them to the end. But for now, feel free to jump in and ask questions as we go along. All right, so this is joint work with my teammates at Google, both members of the TCP team who are listed here and members of the Quick team at Google. And I've just underlined my name here as the one giving the talk. All right, so just a quick outline here. I'll be talking about BBR versions 1 through 3, and then comparing the algorithm to Reno and Cubic, and then providing some information on the current status of deployment at Google, and then giving you some links for further information or how to do experiments. And yeah, well, and then we'll take questions at the end. So without further ado, let's talk about BBR version 1. So what was the history here? What was the motivation? Well, the high-level motivation here was that we noticed a number of problems with loss-based congestion control. So this all goes back to 2011, when many people across the networking community reported lots of problems with excessive buffering and high delays on the public internet. And this problem was given the name buffer bloat. So you've probably seen that buzzword. And in 2012, people started to note that single connection HTTP2 was much slower than multi-connection HTTP1 on links with packet loss. And then by 2013 at Google, we were starting to see poor TCP throughput on wide area networks with commodity shallow buffer switches, which is a characterization that describes Google's B4 network, which has been published in SIGCOMM, but is basically a high-speed, long-haul, wide area network that is built out of commodity shallow buffered switches. And then the culprit for all of these observed phenomena is the same. That is loss-based congestion control. And that includes both Reno, which is the original congestion control for the internet developed in the late 80s and is still the official internet standard as an IETF standard. But that also includes Cubic, which has been the default congestion control for Linux since around 2006 or 2008, somewhere in there. And for these loss-based congestion control algorithms, the problem is that packet loss alone is not really a good proxy to detect or infer congestion. And what happens as a result is that loss-based congestion control is really very overly sensitive to losses that come before sustained congestion. So for example, to achieve 10 gigabit throughput over a 100 millisecond round trip time, if you're using cubic, you need a packet loss rate that is, you know, a tiny fraction of a percent. I think it's 1 in 30 million packets or something like that. Whereas if you consider what is achievable with a more feasible loss rate, like say 1% over 100 milliseconds, that can only achieve about 3 megabits per second per connection. And then that's one class of problem, which is low throughput over high BDP paths with reasonable loss rates or achievable loss rates. The other kind of problem that you can run into is that if a path has deep buffers and low loss rates, then loss-based congestion control will keep ramping up and cause buffer bloat and high delay in such scenarios. So this is just a picture for context of one of Google's data centers to give you a sense of the scale of these kinds of operations. So let's take a drill down into the dynamics here to sort of understand what's going on with loss-based congestion control, why it has these problems, and how we might do better. So the nice thing is that you can understand a lot of these effects just by thinking about a very simple model of a network path.
Neil, I will just interrupt us for a second. At least here, we see only the white screen. We don't see any figures. I don't know if that's the
interesting. So it's just white?
Yes.
Huh. Okay.
Okay.
Did you see the previous slides?
The previous slide, no, it was all white.
Oh, all of the slides so far have just been white?
No, just the previous and one. But now we have the bottleneck and the sender and receiver.
Oh, you do have that now.
Now,
Okay.
yes.
Okay, so I guess the slide images are uploading quite slowly. Is that what I'm to take from that? Let me just do a quick. Okay, my Wi-Fi seems okay. So I'm not sure what's going on. Let me make sure my upload speed is okay. In the meantime, I'll keep talking, I guess. So this is a nice simplified abstract model of a network path. That's something like you may have seen in the original Van Jacobson paper on congestion control in the late 1980s. And in this kind of abstract model, my speed test says I have 35 megabits upload bandwidth. So I'm not sure if this is some sort of Zoom issue or what. Anyway, so this is a sort of abstract representation or model of a network path with this data sender over on the left and a data receiver over on the right. And on the top, we can see the data packets flowing from left to right. And every network path has at some point along it a bottleneck, which is the slowest hop along the network path. And at that hop, if the data sender is sending faster than that bottleneck can forward packets, then you start to get a queue that builds on the upstream end of that bottleneck. And then as we see the data packets make their way to the receiver, and then the receiver typically sends acknowledgements every so many data packets, those ACKs make their way back across the network to the sender, who uses those ACKs to decide what to do with its sending rate and then sends more data. So that's sort of a nice, simple, abstract model of a network path. And if we think about how that behaves, we can use some diagrams like the following to sort of analyze the behavior. So here we have two different diagrams. Both of them have on the x-axis the amount of data in flight in the network at a given time. And the diagram on the bottom is showing how the delivery rate evolves, and the diagram on the top is showing how the round trip time evolves. And we can think about this diagram by imagining a single, say, TCP connection as it starts its life over near the right edge of this diagram, as it starts with a default initial congestion window of, say, 10 packets, which tends to be pretty small for links these days. And as it ramps up its sending rate, it's going to move to the right on the x-axis, putting more and more data in flight on the in the network. And as it does that, its delivery rate will increase. But initially, its round trip time for a long time will be nice and level. And those things are happening because these extra packets are filling up slots in the bottleneck link. and allowing it to achieve a higher delivery rate. But until it reaches some point here that we call the bandwidth delay product, at that point, the behavior will change. And at that point, basically, the sender has reached its maximum sending rate that it can sustain because it has fully saturated the available bandwidth on the bottleneck link. And as it goes to the right here, placing more and more packets in flight, those packets are ending up in that bottleneck queue that we were looking at. And that's going to cause longer and longer delays, queuing delays at the bottleneck queue, causing the RTT to grow linearly with the amount of data in flight. Until finally, a loss-based congestion control will always, with enough data, drive the amount of data in flight all the way to the right here, where it will fill up the bottleneck buffer and cause packet loss and maximum delay. And that's what you get with cubic or Reno loss-based congestion control. So we can also look at what would happen in a scenario with a buffer that is smaller. We might call that a shallow buffered scenario. In a case like that, what happens is that the connection, as it ramps up its amount of data in flight to just pass the BDP by only a small amount, it will then suffer generally it will then suffer packet loss and then cut its C-wind or congestion window that governs its sending rate multiplicatively by a large amount, 50% for Reno, 30% for cubic, and that will tend to, over time, drive the amount of data in flight to be a small fraction of the BDP, causing the flow to use a small fraction of the bottleneck link's available bandwidth. And that leads to poor utilization. So if we ask, what do we actually want in a scenario like this? You know, you've probably already intuited that really the operating point that we'd like to achieve is the bandwidth delay product. That's the point where we've reached the maximum delivery rate, but we've also got the minimum queuing delay. And there was a lot of nice work done in the 1970s by Leonard Kleinrock at UCLA and his grad students, done sort of analyzing these things theoretically and proving, analytically, that indeed this is the optimal operating point for a network. So how could we estimate that optimal point for operating your flow? Well, one thing we can note here is that the bandwidth delay product is the maximum bandwidth that's achievable times the minimum round trip time of the path. And then we can ask ourselves, well, how can we estimate those points? Well, so one way to do it, one way to estimate the minimum round trip time is to take all of the recent min-RTT samples that we've measured and then use a windowed minimum of those RTT samples to estimate the minimum round trip time. And then analogously, one thing we can do to estimate the maximum bandwidth is to use a windowed maximum of bandwidth samples that have been recent. And so you can see here in the diagram, we've got the windowed min of RTT samples is this red sample here. And the windowed max of the bandwidth samples is this red bandwidth sample here. And you can see in this case, at least, those estimates are quite close to the true corresponding values. So we can form estimates in that way, but one interesting thing to keep in mind here is that in this space of possible X values of possible amounts of data in flight, we have sort of two different regions. On the left of the bandwidth delay product, we're in this region where only the minimum round trip time is visible because we have a small amount of data in flight and we're keeping a minimal RTT, but our delivery rate is not really reaching the maximum available. And then on the right of the BDP, we have this region where we can really only measure the maximum bandwidth. We can't measure the minimum round trip time because there's some non-zero queuing delay here. So if we want to measure both, then we have to have our network flow spend some time on the left and some time on the right. And that, in a nutshell, is what BBR version 1 does. So BBR here stands for bottleneck bandwidth and round trip propagation time. Those are sort of the two key model parameters that we were just discussing. And what BBR does is it models the network path explicitly, and it dynamically estimates the windowed maximum bandwidth and minimum round trip time on every ACK that it receives. And then it controls its sending based on that model in order to sequentially probe both the maximum bandwidth and the minimum round trip time to feed its explicit model samples to keep that model up to date. And then it paces the sending of data near the estimated bandwidth, and it varies that pacing rate up and down to probe the properties of the network while keeping the amount of data in flight close to the BDP to keep the queuing delays bounded to a reasonable range. And at a high level, its strategy here is to seek high throughput with a small bounded queue. And in BBR version 1 in particular, it's able to do that and approach the maximum available throughput for random losses up to around 15%. And it's also able to maintain small queues that are bounded to a reasonable level, no matter what the buffer depth is, even in bloated buffers that are common on the edge of the public internet. So that was BBR version 1. And BBR, as we've gained experience and had time to tune it, has evolved over the years into newer versions. So in BBR version 2, that's a version of the algorithm that we released on GitHub in 2019. There were a couple new things and some things and some core aspects that stayed the same. So some of the properties that we maintained since BBR version 1 are the core properties where you can achieve high throughput with a targeted level of random packet loss. And then second, you can still maintain a bounded queuing delay despite bloated buffers. So those core properties we've maintained, but we've made some improvements relative to BBR version 1. So we've improved coexistence when BBR flows are sharing a bottleneck link with Reno or Cubic. We've achieved much lower loss rates for cases where the bottleneck buffer is roughly 1.5 BDP or smaller. And we've improved the throughput for paths with high degrees of aggregation. Here, most commonly Wi-Fi, but also cellular and DOCSIS links have these properties. Also, BBR version 2 can use ECN or explicit congestion notification signals in environments such as data centers or high-speed private WANs, where you're able to configure DCTCP or L4S style ECN signals so that your routers or switches can explicitly signal congestion. And then finally, we've really reduced the throughput reduction that BBR has in a particular mode in its state machine called proprietary. And then BBR version 3 is a version of the code that we released just last month and announced at the ITF in July. And here, you can think of it as sort of a minor evolution of BBR version 2 with two particular areas of improvement. One is two major bug fixes, one for bandwidth convergence with loss or ECN marks. And then the second is bandwidth convergence without loss or ECN marks. And I'll go into a few details here in a second. And then the second major area of improvements in BBR v3 is some performance tuning that we did. And I'll go into a few more details here. So the first bug fix for BBR v3 was that it fixes a bandwidth convergence bug that we can sometimes see when there is loss or ECN. And so we have two pictures of or diagrams of the bandwidth utilization for 4 different BBR flows when they're competing over a 50 megabit link with min RTT of 40 milliseconds. So on the top, we see the bandwidth shared before the bug fix. Two flows enter first and then two flows enter afterward. And you can see they don't really converge to a reasonable fair share. After this bug fix, there is somewhat reusable convergence to a sort of approximate fair share that we would expect from a well-behaving congestion control algorithm. Similarly, there was a second bug that could cause bandwidth convergence in some cases to not occur when there's no loss or ECN, and that was fixed as well. So here again is a similar diagram, but with a much deeper buffer. So there's no ECN, so there were no explicit loss or ECN signals. And we can see in this case on the top, the bandwidth did not converge very well, whereas after the bug fix on the bottom, there was pretty reasonable convergence. So that gives you a sense of those bug fixes. And then the second area of improvement for BBR-v3 was performance tuning. And we made a number of minor performance tuning adjustments. Just to go over them quickly, you can sort of dive into the links here for more information if you're curious. But there's a mode at the beginning of BBR called startup, where it is rapidly probing the network, exponentially growing its sending rate to try to find the available bandwidth in an efficient manner. And we've changed the constants used for computing both the congestion window and the pacing rate. And if you're interested in the details, you can follow the links in the slides to see the analytic derivation that motivated these. We also found that experimentally those worked quite well and did provide performance improvements. There were two other small performance tuning changes. One is to tweak the way that we set some of the internal parameters based on the packet loss signals that we're seeing when we exit startup. And then finally, if we sort of think about the high-level impact of all of these performance tuning changes, they all basically have the effect of lowering queuing delays and packet loss rates during startup and at the point where we are exiting startup and shortly thereafter. And experimentally, we found that all of these changes worked quite well on YouTube, and so they, the experience on YouTube sort of backed up our analytic derivations and gave us some nice results. All right, so that's BBR version 3. The changes. So just a reminder, the properties at the end of the day that we have with the latest version of BBR, which is for v3, is that BBR version 3 can achieve full throughput with up to 1% random packet loss, and that is due to a design, an explicit design parameter choice. Again, it can achieve low queuing delays no matter how deep the bottleneck buffer is. It's able to use ECN signals to keep delays and loss even lower when those ECN signals are available. And it has coexistence with Cubic and Reno that provides usable throughput for both algorithms, BBR and the incumbent algorithm, in the most common internet and data center scenarios. So just a quick summary, because we've sort of zoomed through a couple different versions of the algorithm. We can sort of compare Cubic and BBR version 1 and version 3 with a little table like this to sort of summarize the properties of the algorithms. So if we think about the first row here, the model parameters to the state machine, Cubic, of course, doesn't really have a network model that it's working with. It just has a congestion window. BBR version 1 has the maximum throughput and minimum round trip time model parameters. BBR version 3 expands those with explicit model parameters for the amount of aggregation that the network path is showing, as well as the maximum amount of in-flight data that a path can sustain without causing excessive loss or ECN mark rates. And then in terms of treatment of loss here in the second row, Cubic basically will reduce the CWIN by 30% on any round trip time that has packet loss. BBR version 1, over long time scales, doesn't have an explicit loss response, whereas BBR version 3 does have an explicit loss rate ceiling. When it's probing for bandwidth and it sees a loss rate of 2% or higher, it will explicitly slow down. If we think about ECN behavior, Cubic can be used with RFC 3168 or classic ECN. BBR version 1 did not have any ECN support. BBR version 3 does have ECN support for ECN that is in the vein of DCTCP or L4S. And then if we think about behavior in startup in this last row, Cubic has a mechanism called high start that allows it to exit slow start based on round trip time increases. And of course, it will also exit slow start when there's any packet loss. BBR version 1 will exit startup if the throughput reaches a plateau, indicating, suggesting that it has saturated the bottleneck bandwidth. BBR version 3 has that plateau mechanism, but also will exit startup if the ECN or loss rate is above the target. So if we look under the hood a little bit at the architecture of BBR, it's useful to think about a diagram like this one. So here's the sort of big picture of the components of BBR if we think about them at an architectural level. So at the top here, we have the input that's going into the algorithm. And these are basically different kinds of measurements of network traffic. This includes throughput and delay and loss and ECN. And those measurement inputs are fed into the network path model. And here in the gray, we have the BBR model-based congestion control algorithm, where the subcomponent on the left is the network path model. And then those model features or parameters are used by the state machine that then makes decisions to choose or select 3 control parameters here that are the outputs of the algorithm. And those control parameters are the rate or pacing rate, the volume of in-flight data that's allowed, which is the congestion window, and then what we call a quantum, which is basically a maximum packet burst size that we would like to use, because modern high-speed transport stacks need to use some kind of burst so that they can send a large amount of data every time they run the transport and congestion control loop. Every time through that stack, they want to send a large burst so that they can make a fewer number of executions of that transmit path. And so that's what the quantum parameter is about. So those are the 3 control parameters, and those all get fed into the core transport stack sending engine, which is basically taking the stream of sender data that's written into it, say, with socket system calls in a Linux TCP context. And then that sending engine takes those control parameters and that input data, it slices the input data into packets and bursts of packets, and then it paces out those bursts of data packets. So that's basically the high-level picture of the pieces of the algorithm. And then just to give you a brief overview of the state machine of the algorithm, it basically starts in a phase called startup that we were just talking about, which really rapidly, exponentially, that is, doubles the sending rate every round trip time to quickly reach the maximum throughput of the bottleneck link. And then after that, it enters the drain state to try to reduce the amount of data in the network to drain the data queued at the bottleneck link, if any. And then it enters a phase where it spends most of its time in a state called probe bandwidth, where it's repeatedly cycling the pacing rate to be higher and lower to try to keep an up-to-date estimate of the maximum bandwidth supported by the network path. And then occasionally, if it needs to, it can slow down to probe the round trip time of the network path. So that's kind of a lightning overview of BBR and the history of BBR. So let's take a step back then to compare BBR relative to other congestion control algorithms that have been deployed at scale on wide area networks and the public internet. So the first of these is Reno. This was the original algorithm from the late 1980s, developed by Van Jacobson when he was at Berkeley. And it's still the official IETF standard for wide area congestion control on the public internet. And you're probably familiar with how it works because this is the one that's covered in any networking undergrad textbook. But basically, it starts in a slow start phase where it starts at the initial congestion window configured by the OS and then doubles the congestion window every round trip time until it encounters a packet loss, at which point it will cut the C1 in half. And then it will enter a phase called congestion avoidance, where it linearly increases the congestion window by 1 packet per round trip time until it hits a packet loss, and then it will repeat. And so Reno, at a high level, because of these dynamics, has a brittle loss response and it has non-scalable growth. And what do we mean by that? Let's drill down here. So it has non-scalable linear growth because it's only adding 1 packet per round trip time. So that means that if you upgrade your network and you have 1,000 times more bandwidth, then it's going to take 1,000 times longer to reach full network utilization after every packet loss. And as a consequence, that means it's brittle. That means to fully utilize a 10 gigabit, 100 millisecond path, you would need more than an hour between any packet losses that a given connection sees, which means you need an insanely tiny loss rate that is 2 times 10 to the minus 10. So it's really, really tiny, and which is really basically impossible to achieve. And so that was one of the motivations for introducing Cubic, which is a slightly better congestion control algorithm, slightly better at maintaining high throughput on these high throughput long distance paths. So Cubic is similar in its slow start behavior, and where it differs is in its congestion avoidance behavior. Where Reno had a slow additive increase, Cubic grows its congestion window with this cubic style curve that allows it to grow the congestion window up quickly, relatively quickly, up to the point where it most recently experienced packet loss, and then increase at first slowly after that, but then more and more rapidly as it proceeds without encountering loss again. But here, at the end of the day, Cubic still has performance that does not reach our goals that we have at today's speeds and today's demands for bandwidth. So basically, the growth of the C-wind, although it does use a cubic curve, it still does not have great scalability properties. So again, if you upgrade your network to 1,000 times higher bandwidth, you still need 10 times more time to reach your full throughput after every packet loss, which is still a long time. And so as a consequence, to fully use our sort of benchmark 10 gigabit, 100 millisecond path, you need more than 40 seconds between any packet losses. So of course, that's a big improvement over needing an hour between packet losses, but it's still a very long time. It still means you need a still infeasibly small loss rate. So we can contrast Reno and Cubic with BBR version 3 here, the latest version of BBR, which is able to achieve a bounded loss tolerance and more scalable growth. So how does it do this? It has a scalable exponential growth that can use newly available bandwidth in an amount of time that is on the order of the logarithm of the BDP, which allows it to much more quickly utilize available bandwidth. And so to fully utilize our benchmark 10 gigabit, 100 millisecond path, you can actually have packet loss rates up to the loss threshold in every round. So for the current BBR version 3, you can have up to about 1% random packet loss in every round trip time and still fully utilize your path. All right, so that's a good summary of some of the major WAN congestion controls and their properties. Just to give you a sort of overview of the current status of BBR. So at Google, the current status of BBR is that we have fully deployed BBR version 3 for all of our TCP traffic that is internal to Google and over our wide area network. So you can think of it as basically between Google's data center buildings over the wide area. We use BBR version 3. Within Google data centers, we use a BBR variant that we call BBR.Swift, which we've talked about at the IETF, and you can follow the hyperlink in the slides. And that's basically a version of BBR v3 that has an additional signal that it uses as the primary signal for sensing congestion within the data center. And that signal is the round trip time delay. And when the key mechanism here is usable because when you're within a data center, you can actually know a priori the round trip time that you expect, because data center topologies at Google are very, very regular. So you know what round trip times correspond to congestion and which ones don't. If you see a round trip time that's high enough to indicate congestion, you can slow down in proportion to that excess delay. So for Google external traffic, BBR version 3 is the TCP congestion control we use for all of our google.com public internet traffic as of recently. And then we are doing ongoing A/B experiments comparing version 3 and 1 for a small percentage of users for TCP for YouTube, and then for the new quick transport protocol for both google.com and YouTube. And as we get as these algorithms are tuned a little bit further, we expect those to transition to BBR version 3 as well. So what sort of impacts are we seeing on performance as we transition to BBR version 3? We're seeing lower retransmit rates, so about a 12% reduction. And we're seeing a slight latency improvement for both Google web search and starting YouTube videos. And those latency wins, basically, they seem to be from a lower packet loss rate, which allows for fewer loss recoveries and faster loss recoveries when we do need to recover loss. So this past month, this July, we released BBR v3 as open source, both GPL version 2 and BSD. And you can follow the link here to find the source code. The main updates since version 2 are the ones described in this presentation earlier. It's open source and available for testing. We're going to be working on getting these patches into mainline Linux as soon as possible. Now, the deployment model here is that we are going to be replacing the BBR version 1 code in the module called BBR with the BBR version 3 algorithm and code. And so why are we upgrading it in place rather than creating a separate congestion control module? Basically, that's because the new code, BBR version 3, has better coexistence with Reno and Cubic, the classic incumbent or legacy congestion control protocols. It also has lower loss rates than BBR version 1. It has lower latency for short requests in our experience on google.com and YouTube. And it has throughput that's very similar to BBR version 1. So if I wanted to give a couple notes for those of you out there who are interested in experimenting with different TCP congestion control algorithms to see what kind of performance results you can get. And there are basically two ways that you can go about it on a Linux box. You can enable a different congestion control manually for sort of one-shot experimentation for the rest of the time that particular machine is running before it reboots next. And you can do that just by using the sysctl command line tool, with that command listed there to set the TCP congestion control to be BBR. Or if you want a more permanent solution that will enable BBR every time a machine boots, then you can add the following to your etc sysctl.conf. You can say congestion control equals BBR. And then a second setting that we recommend is to change the default queuing discipline to the FQ queuing discipline, which I'll discuss here in a sec. And then if you're interested in, where and when can we use version 1 versus version 3, here are the details. Basically, BBR version 1 has been in mainline Linux since Linux kernel version 4.9 in December 2016, and version 3 has been available on GitHub since last month. And then a quick note on pacing options here. So BBR always needs and wants pacing, and there are two basic approaches that you can use for providing that. The recommended method is to use the FQ queuing discipline. And now a queuing discipline is a piece of software on a Linux machine that controls the way packets are queued as they are sent out of the network interface card. And we recommend the FQ queuing discipline because it implements both pacing and fair queuing between connections in a way that's scalable and high performance. But if you don't choose to use the FQ queuing discipline, that's fine. In that case, if FQ is not present, BBR will effectively detect that, and it will use the TCP layer pacing that's available in Linux TCP since version 4.20 in December of 2018. And we just recommend FQ because it's a slightly more efficient pacing implementation, and it also gives you fair queuing, which can keep latency low for latency sensitive traffic, even in the presence of throughput seeking bulk traffic. So in conclusion, we've last month open sourced BBR version 3 with some significant bug fixes and performance tuning. And it's currently being used for all of Google.com public internet and internal WAN TCP traffic. So it has a lot of air miles on it, and we have high confidence in it. So you're welcome to test it out. It's under testing for YouTube traffic and click traffic. And we're going to work on getting it into mainline Linux, and we're going to work on updating the BBR internet drafts to cover version 3. And, we invite the networking community to take all of this out for a spin and provide feedback on the algorithm or the code or the internet drafts, and share any test results or issues or patches or ideas you might have. Thank you very much. And it looks like we might have a few minutes for questions. Any questions out there?
Thank you, Neil. I don't see any yet. Meanwhile, I have a one. You mentioned buffer size, and BBR version 3 is working well with large buffers, avoiding buffer bloat. So did you measure what is the impact of the buffer size when it's pretty large on fairness? For example, if you have Cubic and BBR version 3 running together.
Right. So we've done basic experiments on this, and the basic dynamic is that the larger the buffer depth, the larger the share of bandwidth that Cubic will grab. And at moderate buffer sizes that we would, that most people would recommend, that's sort of on the order of a bandwidth delay product. It's not a big deal, and you can get reasonable levels of bandwidth sharing. It's when you start to get into buffers that are many times the bandwidth delay product, the basic dynamic is that Cubic will try to fill all of that buffer space, and if it has enough data, it will succeed. And so you'll tend to get lots of Cubic data clogging up those buffers and grabbing a large share of the bandwidth. So we basically do recommend that people keep their buffers of more reasonable size, around a BDP or so. And in that case, most of our tests show BBR getting a reasonable fraction of the throughput.
Thank you. There's a second question in the chat window.
Let's see, what's the... I see one new message button. It's weird that it doesn't. Let's see. I know that BBR, at least some version, exists in FreeBSD. Yeah, so there is a version of BBR that is in the BSD TCP stack. It's a sort of optional, separate, I think in BSD they call it a separate TCP stack, but it's sort of like a modular TCP implementation that you can choose to enable. I know that was implemented by Randall Stewart and others at Netflix, and they've done experiments with it and had decent results. So that is something that is usable if you are a FreeBSD site. That's absolutely something you could take out for a spin. And I know the Netflix people have used it, so it's probably reasonably solid. Oh, I see another question here. So do I understand this right, that BBR3 solves the buffer bloat problem, i.e. does it replace CODA-like mechanisms? Yeah, so So yeah, so all the versions of BBR aim to, as one of their attributes, they do try to, avoid buffer bloat problems. And so you can think of it as a replacement for a coddle-like mechanism. That is, if you're running BBR, then you shouldn't need coddle to control the delays at your bottleneck. However, coddle and FQ coddle are quite nice, and there's no reason not to use those. And in some cases, they can give you slightly lower delays because coddle is essentially coddle is operating with more information than BBR has, because coddle is able to see all of the traffic going through the bottleneck, and then B, coddle is seeking a particular typical delay that, if I recall correctly, is on the order of 5 milliseconds, which can be lower than the delay that you'll get if you've got multiple BBR flows competing at a bottleneck over a WAN path. So the short answer is yes, BBR is trying to avoid buffer bloat. So it can replace coddle-like mechanisms if all of the flows are using BBR. But since you don't always know that all of the flows are using BBR, you may as well deploy FQ coddle in particular. And then if you're running BBR, then that will just be, a belt and suspenders defense in depth against buffer bloat. Any other questions out there? All right.
I don't see any. Well, Neil, thank you very much again. I think that your slides are already posted. If somebody wanna take a look. So thank you very much. We appreciate being here.
Absolutely. Thank you very much for the chance to talk to you guys. I appreciate it. Take care. Bye.
Okay, and we will have a break of 15 minutes. We will be back at 2:45, and we'll have our first hands-on session, monitoring buffer occupancy using P4 switches. So I will pause the recording right now, and again, we'll be back in about 15 minutes. Right, we're back for hands-on session number 3 of this workshop, monitoring buffer occupancy in P4 switches. And this session will be led by Eli Kafuri from the University of South Carolina. Eli is assistant professor here in the College of Engineering and Computing. And Eli, at this point, I will let you share the screen and so you can lead the session.
All right, sounds good. Thank you. Okay, just want to confirm, can you all see my screen?
Yes.
All right, thank you. So in this session, we're gonna be looking at how we can write a P4 program to monitor the queue occupancy. And there has been a lot of talks today about buffers and queues. So I'm just gonna make this short. The idea here is whenever we have a switch or a router, it has a queue, it has a buffer, and that buffer is used to accommodate the transient burst of flows. So whenever we have some rates that exceed the bottleneck link, for example, if you have 1 gigabits per second bottleneck link, and you have an input rate that is higher than that, the queue will start building up. And whenever you have a queue build up, this would affect the end-to-end latency. Because now if you calculate the round-trip time, your packet is gonna be spending some extra time in the queue because of how the queue is being filled. Typically that queue, the time that the packet will spend in the queue is in the order of microseconds to milliseconds. So how can we calculate the queuing delay in P4? So in many target, and by target I mean P4 switch, whether it is
Lee, can you hear us? We lost you, I think.
Can you hear me?
Now I can hear you back.
Okay. All right. So yeah, as I was saying, the queuing information is provided to us by the architecture. And so basically, in this lab, we're going to be using the BMV2 software switch, and that switch has a V1 model architecture. And this model is appearing here. So as part of the ingress pipeline, we would have access to some timestamps. And in the ingress pipeline, we also have access to timestamps. And then we can leverage those timestamps to basically compute the queuing delay. So some of the fields that we're going to be using, something called in-queue timestamp. This is the timestamp that is basically provided to us whenever a packet is first entering the queue. And also we have the egress global timestamp. This is the timestamp when the packet first enters the egress pipeline. And that would basically, with these two timestamps, we can compute their difference, and then we will be able to find out the delay or the queuing delay and how much time the packet has spent in the buffer. Also, as part of this standard metadata, sometimes they call them intrinsic metadata in some architectures, we also have a field which tells us the queue depth in packets. So we can know how many packets exist in the queue for whenever we are processing the current packet in the switch. So in this lab, this is how the topology looks like. We have 4 hosts, H1, H2, H3, H4. We have one P4 switch, S1. And we have a regular switch, non-programmable switch, S2. And the goal is to observe the queue occupancy on the switch S1 here. So to do so, first we're going to be limiting the rate to 100 megabits per second. So this is going to be the rate here at the output interface facing S2 on S1. And then we're going to run a throughput test using iPerf from H3 to H4. So with that throughput test, because we limited the bandwidth here, we're going to have a bottleneck. And because of that bottleneck, our queue is going to start being utilized in the switch. At the same time, we're going to be sending packet probes from H1 to H2. And these probes will use a custom header that we will define in our P4 program. And it's the job of the switch to insert the queuing information in that custom header. And then later on, we're going to be able to see the information related to queuing in the collector here, which in our case is H2. So H2 will receive these probe packets and will display the values inside the header fields. So the custom header that we're going to create looks like this. First, we have a switch ID, which is 8 bits. This is kind of optional, but if you have a large topology and you want to identify which switch is being processed, or the queue of which switch is being processed, you can insert it here. So in this example, we can have the value 1, but if you have multiple switches, it can be 2, 3, and so on. We have the in-queue timestamp. This is going to be 32 bits. This is when when the packet is first in-queued. The dequeue timestamp, 48 bits. The queuing delay, which is essentially the difference between these two timestamps. And finally, the queue depth, which is the number of packets in the queue. Now, regarding the sizes here, typically we have to follow what the architecture gives us. So in this V1 model, the in-queue timestamp is 32-bit, but the dequeue timestamp is 48 bits, and essentially we just have to follow them. Now, our custom protocol will be placed on top of IPv4, and therefore we're going to be also specifying some value for the protocol field in IPv4. Typically, this is how we know what is the next protocol after IPv4. And we're going to hard code it to 0xFD. So we'll assume that if the protocol field in IPv4 has 0xFD, it means that this is a probing packet. This is some information to access the platform. So we're going to be using NetLab. The link is here, and we're going to also place it in the chat. If you already created an account from last session, last week, you don't have to repeat the steps in creating the account. But if you didn't do any hands-on last week, feel free to log in by using your email address, the one that you use for registration. and the temporary password NSF 2023. When you first log in, it will ask you to provide a new password, to change the password, and then you'll be able to use that password for all your lab activities. Next, once you have your account ready, we're going to be able to schedule a lab. And in this session, we're going to be using this course topic before applications and custom processing. We have two of them. The first is for the introductory labs, and for the labs that contain more information about custom package processing, they're going to be found in this one. So for this session, we're going to use the before applications and custom processing. And specifically, we're going to do lab number 5. I will go over all these steps when I do the reservation, and just giving you some information before we do so. Okay, we allocate some time for our pod, and then we will start. All right, so the URL of the platform is provided on the chat, so feel free to click on it, and then we can do a reservation. I can see that some of you already created the reservations. If you didn't, you can follow my steps here. We'll first start by creating a new lab reservation, schedule a lab for myself. And then you're going to be seeing these course topics. So we're going to select before applications and custom processing. And then these are all the labs in this library. We're going to be just using here lab number 5. Okay, so you can see here we have the available pods. They are the ones that are seeing right now are being used, but you have this arrow button. You can click on it so that you can see more available pods. So go ahead and click right on the red line, and then make a reservation. You can select maybe like for an hour or hour and a half. But if you selected less than that, you can still expand once you are reaching the end of your reservation. And then we click on submit. And now we should be able to see our reservation. All we have to do is click on enter lab, and our pod will start initializing. Okay. So when you do the reservation, you enter to the pod, you're going to see this screen here where you have a client. This is the environment where we're going to be developing our P4 program and running everything into an emulation. You can see here also we have the content. So you can click on the arrow undock so that we can see the hands-on instructions. You can put it on the left-hand side and then put the platform on the right-hand side. This way we can see both screens at the same time. Okay. Now, how does the lab look like? We have the table of content that will describe what's inside the lab, some general information, overview, objectives of the lab. Here we have a table for the credentials. We only have one device, so we only need to use password all small caps. So whenever we have to input any password, it's going to be password all small caps. Some background about queuing delay and how we can compute it in P4, but we're going to skip that and just start immediately with the section number 2, where we do the hands-on part. All right, so I will enter to the client. And from here, we're going to start with step number 1. So we will launch mini edit, which is on the desktop. So I'll click on mini edit. It's asking us for the password. The password is password all small caps. Once you enter the password, mini edit will launch. And mini edit is just a graphical interface for Mininet. You can create your custom topology by dragging and dropping these elements that you see on the left-hand side. But instead of creating the custom topology, we're just gonna load it since we already created them for you. And this way, we'll save some time and just open a pre-created topology. So we are doing lab number 5, and therefore we're gonna go to lab 5 and then load the topology of lab 5. As you can see, it's close to what we discussed in the slides. So one P4 switch, the other is a legacy regular switch, and then we have 4 hosts connected in that topology. Next, we're gonna start the emulation by clicking on the run button, which can be found at the bottom left of the screen. All right, now the topology has started. You can see we can no longer drag and drop devices. This means that our emulation has started, and now we're ready to start writing the P4 program and testing it. So I have a question on the chat, what to do after reservation. So, okay, I will go to the screen here. So essentially what you see after you do the reservation is a screen like this. Okay, and you will see here your reservation that you just created, and there's a button called Enter Lab. All right, so all you have to do is just click on Enter Lab, and then you can undock the content and then put it on the left-hand side like I did. And then you click on Client so that you have your environment on the right. All right, so another comment is that there is no button. Okay, so if you have that issue, this means that when you created a lab reservation, okay, and I'm gonna show you here. When you created the lab reservation, it seems that you did not click right on the red line. You allocated a time for later, right? So what I would suggest is you can create another reservation. We have enough pods. And then once you do the reservation, make sure to click right on the red line. This means that you want the reservation to start right away and not scheduled for a later time. All right. Okay, thank you. Let me know if you have any problems. And there's also Jose here who can help you if you have any trouble with logging in. So I will go back to my reservation. Okay, so now in section number 3, we're going to start the programming environment. We're going to do so by starting a terminal, which can be found on the desktop. And there, we're going to type in this command, code for _labs, lab 5. So code, this is our editor that we're going to use, Visual Studio Code. And then we are specifying the location where we want to open our current directory in that editor. So I specified lab 5. This means that I want to operate on the lab files of lab number 5. Right? You can see that now I'm at lab number 5. On the left-hand side, you have the file explorer. So these are all the files that you can edit or see that has to do with your P4 program. And also you can see that we have an integrated terminal in that editor. This will allow us to compile the program right away instead of going back and forth with the command line. All right, so the first step is to define our custom header. And this is gonna be done in the headers.p4 file. So we click on headers.p4 and you will see basically here how your header file looks like. Let me just undock as well, and just to make it a little bit clearer. All right, so what you can see here is that there's already some code inside that file. For example, there's a header for the Ethernet, there's a header for the IPv4 already created, and we are free here to create our own custom header. But before we do so, we're gonna be creating a constant here for the type, which we're gonna be inspect in the protocol field of the IPv4 header. So if you remember in the slide, we said that we're gonna use this value 0xFD. And once we parse that, or once we match on that field in the protocol of IPv4, we know that we have a probing packet. So first, let's create that. So it's gonna be an 8-bit. We're gonna call it type_custom for our custom protocol. And then it's gonna have the value 0xFD. Okay. Next, we're gonna start by defining our custom header. So the same as what has been done for the Ethernet and IPv4, we can create our own custom header. So we start by using the keyword header, and then we give it the type that we want to use later on when instantiating from this header. So we're going to call it switch stats for switch statistics _t, just to denote that this is a type, and we're going to instantiate from it later on. Now, what are we going to add to this header, to this custom header? First, we have our switch ID, which is an 8-bit field. So bit 8 switch _ID. Then we have a 32-bit field for the enqueue timestamp. Okay, and by the way, these are all up to you. So we are calling them like that, right? But it doesn't matter. It doesn't have to be enqueue timestamp. Later on, when we access these fields from the standard metadata, you have to use the right words. But here we are just defining, it's like you are defining an irregular variable. Then we're going to be defining a 48-bit for the DQ timestamp. We have a 48-bit for the queue delay. And finally, we have a 24-bit for the queue depth. Okay. So again, at this point, I just defined how my custom header would look like. What are the fields in my custom headers? And we specified that we need to store the ID of the switch, the time the packet is enqueued, the time it's dequeued, what is the queuing delay, as well as how many packets were in the queue when this packet was processed. Okay. Now, the next step would be to instantiate from that header. So if we scroll down, we can see that we have a header struct that contain what are the possible headers that are going to be contained in our packets and all the packets coming to the switch. So we said that first we start with the Ethernet, then we have IPv4 after it. So now we're going to add our new header, which is switch stats. So switch stats _t, and then we're going to call it here switch _stats. So I used this header definition here so that we can instantiate and place it in our header structure. Okay. Now, at this point, we have to save the file. So you can press Control S or file save. Just make sure to save it because we're going to be going to another file to do some further changes. So we created our custom header. Next, we're going to be parsing. We're going to tell the P4 switch how to parse our custom header. So there's a file called parser.p4. This is where we have the parsing logic. You can see we have a state for parsing the Ethernet, state for parsing IPv4. So we're going to be adding basically a new state to be able to parse our custom header. All right, so we start first by using the keyword state to denote that we are creating now a new state. You give it a name. So for example, parse _switch stats. And there we're going to say, how are we going to parse our headers? So we're going to be using the packet. And what is this packet here? If you look at the parameters of this control block, my parser, you can see that this is a packet in. So this is the packet that's being received to the switch, right? So we're going to extract from it, .extract, and then place into our switch _stats. Okay, so the header here is an instance of the headers that we saw before, right? And the type here is out. So we are filling now this header with our switch stats. And then we're going to be transitioning to the accept, meaning that now we're done with the parsing. We can move into the next block, which is the ingress block. All right. Now, at this point, we defined how the state looks like, but how can we reach to that state? Because typically, when your packet is received on the switch, you have to tell the P4 switch that you have to start by parsing this header and then jump to another header and then another header and so on. At this point, we just defined how the state looks like, but we didn't tell the P4 program how to get to that state. And as we said before, we are assuming that this custom header will be inserted on top of the IPv4 header. And essentially what we're gonna do is we're gonna modify the state that is already created for us for parsing IPv4. So we're gonna keep the first line, which extracts from the packet the IPv4 headers. But then we're gonna be, instead of just unconditionally go to the accept and start processing in the ingress, we're gonna remove that and then do some checks. So I will use here transition select, meaning that I want to do some condition. And that condition will be on the field, which can be found under the IPv4 header. So header.ipv4.close. This is very similar to a switch case in C or C++. So I'm saying here, I want to check the value of header.ipv4.protocol. In case that value is equal to type custom, this is what we created basically in the headers file. We're gonna be transitioning to a state called parse switch stats. Okay, so if your P4 switch received the packet and in the IPv4 inside the protocol field, the value was equal to type custom or 0xFD, now we can go to our next state, which is parse switch stats. If not, so in the default case, we just accept and we jump to the ingress pipeline. Okay, so the way you can read this, you start with the start state, you jump immediately to parse Ethernet. There, you extract the Ethernet header, then you check for the ether type. If it is IPv4, you go to the parse IPv4 state. Now we also extract the IPv4 header, then we check. If it is the custom protocol, we jump to the switch stats. Otherwise, we just accept and move into the ingress pipeline. All right. Next, we have to save the file as well, Control S or file save. So at this point, we just defined how the header looks like and how we can parse it, but we did not fill it with the information related to queuing. So this is what we're gonna do in the egress. And the reason we are doing it in the egress, because it's in the egress, we can obtain these timestamps. Okay, so this is after the packet has traversed our buffer and went through the traffic manager. It's very important to do it in the egress because we don't have access to the fields provided by the architecture in the ingress. That's because the packet has not traversed the buffer yet. So in the egress, you can see it's empty. The apply block is empty. What we're gonna do is we're gonna create an action. An action here, you can compare it to like a regular function in C. We're gonna call it here modify. Okay. And then we're gonna write the logic. So what are we doing here? We are modifying the values inside these header fields that we defined in the previous steps. So the first thing we're gonna do is we're gonna set the switch ID. So header dot switch stats dot switch ID. You can hard code it to 1, but if you have a bigger topology, you can also populate these values from the control plane and then basically pass it to the program. But just for simplicity, we're assuming 1 before switch, we just give it the value 1. Then we're gonna fill the next field under the switch stats. And this is gonna be the enqueue timestamp. So what are we gonna place inside that header field? We're gonna be getting the enqueue timestamp from the architecture, and everything that is provided to you from the architecture will be found under standard metadata. Standard metadata, you can see it also passed by default to this control block. So under standard metadata, you have a bunch of fields provided to you. One of them is the enqueue timestamp. Okay. So again, what we are doing here, we are getting from the architecture and then we are putting it inside our custom header. Then we will continue with the next fields. So we have enqueue timestamp and then we have dequeue timestamp. And also we're gonna get the value from the standard metadata, but this time it's called egress global timestamp. So this is the timestamp when the packet first gets to your egress pipeline. Then we're gonna also add or assign the value for the queue delay. So what is the queue delay? It's not provided by default by the architecture, but we can calculate that. And essentially it's equal to the current timestamp in the egress minus the time this packet was enqueued. So this would give you what your queuing delay is. So standard metadata dot egress global timestamp minus. Here I'm casting to 48 bits because the egress global timestamp is 48 bits and the queue delay field is 48 bits, but the in-queue timestamp was 32 bits. So you just make sure to have the right casting so that you can do any of these operations. Standard metadata dot in-queue timestamp. So we have a command. I think there is a subtraction when setting the value of DQ timestamp. Let me see. Header switch DQ timestamp equals standard metadata egress global timestamp. Oh yeah, no problem. Thank you for you know, keeping your eye on, because there's a lot of comments and you know, we might have some typos while writing all of these. Okay, so again, what we are doing here for the queue delay, we are getting the egress global timestamp and then minus the in-queue timestamp. This would tell us what is our queuing delay is. Okay. Finally, we're gonna be also adding to our queue depth. Now remember, queue depth is different than the other in the sense that it's in packets. So it will tell you how many packets exist in your queue. So switch stats dot queue underscore depth equals to bit 24 standard metadata dot in queue underscore queue. Yes. So this is also provided by the architecture, right? It's under standard metadata. All right. So now we created an action, but this action will not be executed by itself. You have to dictate how your actions are going to be executed, or if you have match action table, what is the sequence of execution, by writing them inside the apply block. So all I have to do here is just call my action, which is modify. Okay, so we called it modify here, and now I'm invoking it from the apply. It's kind of similar to you have a function and then you have a main function, and then you within the main you are invoking another function. Okay, so now we can save our file, this egress.p4 file. Next, we're gonna also modify our dparser file. So in the dparser, you can see that by default, we are just emitting the Ethernet and the IPv4. And essentially, when you write in the dparser means that how you want your packet to look like, how are you going to construct it when you want it to leave your P4 switch. So we want to add this switch stats custom header to our packet. And therefore, you have to write here packet.emit header.switch stats. If you don't do that, it's not going to add it to your packet once it's leaving your switch. So packet.emit header.switch underscore stats. And then, of course, we have to save that file, Control S or file save. So at this point, I think we're done with writing the P4 program. We can try to compile and see if we have an error. So the way we compile the program is using the P4 compiler, P4C. And we have our file basic.p4, which is basically instantiating an instance of this data plane, and it's considering all these different blocks inside the files that we saw, like the parser and the egress and the dparser. So P4C basic.p4. Okay, so it seems here we missed the semicolon, modify. All right, so once you don't have an output after compiling, it means that you don't have an error in the compilation process. Now, your P4C basic.p4 compiled the program and generated a .json file. This is the data plane specification. This is what you're gonna be importing to your switch when you run the daemon. It's kind of similar to a binary if you have a real switch. This is basically your specification. So this is the output of your of the compilation process of your P4 program. Next, we're gonna push that file, basic.json, to our switch file system. So push to switch is just a script that would, you give it a file name, basic.json, and then what is the target device you wanna push to in your topology. In our topology, this is S1, so we are pushing the output of the compiler to S1. So as you put a password, the password again is password, all small caps. All right. So now we compiled, we pushed the output of the compiler to our file system on the switch. Next, we can verify the configuration. So I will maximize the mini edit. And then we can enter to each of these devices by holding the right click on the device and then clicking on terminal. So now I'm within the terminal of switch S1. In this step, I will just use ls to list the current directory's content, and we can see that we have basic.json, and that's the file that we just pushed from the Visual Studio Code's terminal. Next, we're gonna start the switch daemon, and then we're gonna map the logical ports understood by the switch to the actual interfaces on Linux. So simple switch, this is the daemon, -i for interface. So port 0 is gonna be S1 ETH0. Port 1 will be S1 ETH1. Port 2 will be S1 ETH2. Okay, and then you give it the data plane specification file or the output of the compiler. So this is basic.json, and we can also run it in the background. This way we can continue working on the same terminal without having to reopen another terminal by using the ampersand. So it tells you that we added the interfaces S1 ETH0 as port 0, 1 as port 1, and etc. It means that your interfaces are added to your ports on the switch. Next, let's press on enter to retrieve back the command line. And the next step would be to populate the forwarding table on our switch. So essentially, we want to do a throughput test and we want to see the queuing occupancy. But before we can do that, we want to make sure that we have the right rules so that the switch here can forward the traffic. So since this is not the goal of this lab, it's already created in a script, and we're just going to be passing that script to the simple switch CLI, which is the control plane interface for the switch that we're using. So simple switch underscore CLI. We can pass to it the file lab5 rules. So lab5 rules contains these forwarding rules that were already created for us. We are just pushing them now to the control, from the control plane side to the data plane on the switch. Okay, and you can see here, it will tell you they all are related to the forwarding. The next step would be to modify the rate of the link. So we said that we're going to set it to 100 megabits per second. In order to do that, we're going to now use the simple switch CLI, but I will enter it interactively instead of redirecting some commands to it. So just type in simple switch CLI, and then you will open the command line interface. You can start issuing commands here. So there is an available command within it called set queue rate. You give it a value here, and this value is in packets per second. Essentially, if you are trying to limit the rate, so you can pass here how many packets per second you want to process. So if you do the math, let's say you want to have 100 megabits per second, right? And let's assume that the packet is 1500 bytes, which is equal to the MTU, or the maximum transmission unit. If you just divide 100 megabits per second over the MTU in bits here, you get around 8,333 packets. So you can say here 8333. This means that you're gonna now get around 100 megabits per second of your link. And again, we are limiting here just so that we can make sure that the queue will be occupied and we can observe the queuing from the P4 switch. All right. The next step would be to set the queue size or the buffer size. So there's a command set underscore queue depth, and then you pass to it how many packets you wanted to hold. Here I will use 1666. How did we get this value? We set it to the bandwidth delay product, BDP, and we assumed a typical delay that we have is 20 milliseconds. So if you multiply 100 megabits per second by 20 milliseconds, you get around 166 packets. But instead of just setting it to 1 BDP, we set it to 10 BDP, and therefore it's 1666 packets. Okay, but this is completely up to you. I mean, you can play with that buffer. You can make it small and see what is the impact on your throughput. You can make it high. It's configurable, essentially. All right, now we can test some configuration. So I will go to the mini edit again, and I will start an Hyper-3 server on host H4. So again, Hyper-3 is just a tool that would allow us to inject traffic and then measure the throughput. It works in a client-server approach, so you would need to start first a server, and then your sender will be the client. So because I will be sending traffic from H3 to H4, I will start a server on H4 by writing hyper3-s, S for server. So now we have a server started listening. Then we can start a test by going to the terminal of H3. So again, you hold the right-click terminal, and from there you can write hyper3-c so that this is executed in client mode. But when you execute in client mode, you have to tell it where your server is. So in our case, it's H4 or 10.0.0.4. That's the IP address of H4. Okay, so we have a test here. iPerf will be executing for 10 seconds. You can see what's important here is the bit rate per each second interval. So from 0 to 1, we have 96.9 megabits. You can also see the transmissions, congestion window. But essentially, the goal here of the step is just to confirm that we were able to limit the rate to around 100 megabits. It's never going to be exactly 100 megabits, but it's close to it. So we have around 95, 94. At the end, you can see here the average. It's around 95.8 megabits. Okay. Next, we're going to start the server on host H2 to listen for probe packets. Because remember, the goal was to start an iPerf server or iPerf test from H3 to H4 and start probing from H1 to H2. Before we start sending the probes, we will start a script that will be listening for probes. So receive.py-p probe. This is just a script that we created that leverages Scapy on Python, and it will basically display the packets. Now on host H1, we can start sending the probes. So I will go to H1, open the terminal, and then use the script send.py. The destination is H2. That's the device going to be listening for our probes. We can give optionally like a payload, hello world. And then we have to specify that we are sending probes here using -p and then probe. So what this script here does is it keeps creating packets, right? You can see this is running in a loop. And it's already creating the header for us, which is the queue stats. This is the one that we want to parse in the P4 switch later on. By default, the fields are all zeros. So they are initialized to 0, and it's the goal of the switch, the P4 switch, to fill these fields here. Before we run the test, you can go to host H2 and verify that you are seeing this information here. Okay. Now we're going to keep those running, but then we're going to start an hyper-3 test again. So I will go back to H3. And then I will start hyper-3. So what I did here, I specified -t to specify that I want the test to run for this many seconds, 120 seconds. And I use also -p 30. This would allow us to run parallel streams, 30 parallel streams. When you have parallel streams, you are creating more load, and then the queue would be occupied more. Okay. And I'll press on enter. You can see we are getting around 100 megabits. But now let's go back to H2 and inspect what's happening here. So you can see that this is the enqueue timestamp, dequeue timestamp, all being filled by the switch. The queue delay, we are seeing it here, right? And then you have the queue length, which is how many packets inside our queue. So remember that we set the queue to be 1,666 at most. So this is what your queue length here. It's not fully occupied, but it's getting there. So because you have this test, you can see it can go up to 600, 700, then go down. Sometimes go even a little bit up. It depends on the dynamic of your throughput test that you are running. Okay. Now, at the same time, if we go to H1 and start another terminal, we can try to ping 10.0.0.4. You can see now we have an increased latency. We did not emulate any propagation delay here. So if there was no test, you would see a very small amount of milliseconds, right? Maybe like 0.01 or 0.5, something like that. Now, because your queue is being utilized and we set a queue to be big enough, you can see here how it's affecting the latency for a simple ping test or round trip time test. And with that, we conclude this lab. If there's any question, please let me know. You can use the chat or unmute yourself.
Thank you, Lee. I don't see any questions. One observation, though, or maybe question is, you're using, I didn't pay attention enough, but you're using Cubic for this test. Is that correct?
Yes, that's correct. This is the regular or the default congestion control algorithm by Linux.
So if, according to the previous presenter, Neil Carville was saying that BBR should be able to limit the rate, so not to suffer of buffer bloat, which is what we are seeing right now. Did you anticipate that? I mean, did you test that? Did you think about that?
Yeah, theoretically, that's correct. That should happen. And if you are testing in a with real hardware, that would definitely happen. Now here for the switch, it's at the end, it's all running in software, and the amount of CPU that you allocate and all of the other interrupts that happen in the operating system will affect that. So you won't have really a very accurate, or if you want to really measure the queuing delay of a certain congestion control, these software switches can give you an idea, but will not give you a very high precise value, basically. But yeah, if you do it on a hardware switch, it will work. And here I believe we are using the regular BMV2, but there's the optimized version which can even go at higher rates, up to 1 gigabits. Maybe with that we can even see the how we are solving the buffer bloat with the BBR even better.
Thank you. Can you hear me, Lee?
Yes, I can hear you.
Yeah, my computer is acting very strange. I don't see any other questions, so we are well in time. Yes.
I think we just, yeah, there's a new question that just popped up right now. And the results obtained for 100 megabits per second can be used to estimate what would happen in 1,000 megabits per second. I would say to some extent, yes, but there are several factors that you have to keep in mind. One, the one that I was talking about, being a software switch with higher rates, means that you are using more processing, and if your CPU becomes the bottleneck, then you have packet losses, and then you won't be able to generalize well. And also, second, a big factor that affects your queuing delay, if you look here at this topology, is basically the input-output ratio for your link speeds. So to give an example, if you are using a link of 1 gigabit in the output here of S1 and your input is 40 gig, this is gonna be different than if you have 40 gig and 10 gig. Okay, this plays a big role in determining how much your buffer is being utilized and what is the queuing latency that you can occupy. So to some extent, you can generalize in the sense that, yes, you can still see the increase in the latency and get an idea, but you have to be careful because there are several parameters involved in this experiment that you have to fine tune. Even, I mean, the buffer size that you want to configure, if you are changing from 100 meg to 1 gig, it means that your BDP is different now. Your bandwidth delay product is different, and then you have to also set the queue size based on your new rates. So again, it all depends on the experiments parameters.
All right, I don't see any additional questions. So thank you, Lee, for this presentation. So we have let's have a 10-minute break, and then we will have the last hands-on session. Jose, would you mind please just putting on the screen, or Lee, that we're going to be back at 3:45, and that will be our last session of the workshop. We will have a hands-on session number 4. We will be measuring packets inter-arrival time with the P4. And Eli, you are a co-host. Would you mind stop recording at this moment?
Yes.
Or just pause? Because we'll... All right, we're back, and we are with the last activity of this workshop. We'll start the hands-on session number 4, calculating packet inter-arrival time with P4 switches. And this session will be led by Ali Alsabe. Ali is a grad student here at the University of South Carolina, and he has been developing some of these P4 libraries. Ali, welcome, and I will let you share your screen.
All right, thank you. So, okay, I think everyone should be able to see my screen. So in this activity, we'll be doing the P4 lab, which is about calculating the packet inter-arrival time, and all the activities in this lab are in lab number 10 of the library P4 Programmable Data Planes, Application, Stateful Elements, and Custom Processing. So this is the part 2 of the P4 library, which is more advanced topics. So the inter-arrival time, it's basically the time between 2 consecutive packets. Sometimes you want to calculate it for IP packets, or let's say TCP, UDP, and it's typically it's not trivial to calculate such inter-arrival time on general purpose CPUs because especially when the rate is high. So let's say you have gigabits of traffic. It's really hard to keep track of the inter-arrival time between every single packet. So with P4, this can be done. So the P4 switches offer a granular timestamp. So once the packet arrives at the switch, you can know exactly when this packet has arrived, and this is basically using timestamps that are offered within the architecture of P4. Okay. So as mentioned, the inter-arrival time can be calculated between packets belonging to the same flow, and with the flow you can basically define it as you want. It could be based on the source and IP, source and destination IP addresses. It could be the 5-tuple, which is source, destination, IP address, source port, and the protocol. So every packet that arrives at the switch, we can calculate the 5-tuple in P4 using hash algorithms, and the cyclic redundancy check, the CRC hash, is provided in the V1 model architecture. Right. So this is just like what happens. Typically, a packet arrives at the switch. Let's say we want to calculate the inter-arrival time of packets belong to the same flow with respect to their 5-tuple. The hash is computed in the switch, and then an index will be be output, and then this index will be stored in a memory. So P4 switches, they have the ability to store data. These are called typically registers or counters. So these are stateful elements. Once a packet arrives at the switch, you calculate the index. And so this is the index here. It's the index of the register in the P4 switch, and then you save the timestamp. So this timestamp here is taken from the P4 switch metadata. So the next time another packet arrives and has the same hash output, which is the same index, it will arrive here, and then we can calculate the inter-arrival time from the current time observed, subtracted from the time that's stored in the register. So this is very useful for a lot of applications. Could be, say, security applications. Could be, let's say you wanna kind of monitor your traffic, see the rate. Okay, so this is our topology. Our topology consists of 4 hosts, H1, H2, H3, and H4, and the P4 switch. And typically what's gonna happen is we will create a custom header. So here, the custom header will be the inter-arrival time. It's gonna be on top of IPv4, and this custom header will store the inter-arrival time. So from host H1, we will send, let's say, a custom packet with the inter-arrival time, and then the switch will store this in the register. So the next time a packet arrives, it will compute the inter-arrival time, and then the result will be output on H2. And so on. Similarly, we'll do the same with H3 and H4 while manipulating the rate on which we send the packets. Okay. So let's move on to the, okay. So I'm in NetLab. It's the same system that Eli was using before. And you should be able to see the workshop on P4 programmable switches, August 2023. So I will go ahead and click on it to make a reservation for Lab 4. And there are 2 parts. I'm now in P4 applications and custom processing. So go ahead and click here. And then I'm doing lab number 10, which is calculating the packets inter-arrival times using hashes and register. So go ahead and click here. There's a question. Do I need to consider hash collisions here? So in our lab, we don't consider hash collisions. It's just a simple, like we have an index and the register, but we don't take collisions into consideration. There are a lot of implementations where you can consider hash collisions in before. So one of them is called cuckoo hashing that I know of. And what you would do is, instead of having, for instance, one register, you would have two registers and then two indices. So if there's a collision in the first register, you would move on to the second register and the check. So you can resolve that in before. It's not a problem. I hope that answers your question. Okay, so you see here there are these reservations already been occupied. What you can do is click on the arrow right here and then just move until you see a free reservation. I'm gonna choose this. Make sure you click on the red line over here, and then you can specify the time. I'm gonna put it until 5 p.m. and then click submit. There's another question. Meanwhile, is the material online and open to us? Yes, if you're talking about all the material that we are covering in this, all the lab libraries are available online, and you can, if you check our website.
And then you might want to point out the virtual machine first, and then the
Yeah. So this is the web page for our website, for our workshop. I'm gonna post it in the group chat. And here you see there's the VM for the P4 labs. If you don't want to use our NetLab, you can download your virtual machine and work. It's perfectly fine. And the materials, all the materials are under cyber training. If you go there, we see we have a lot of labs. In this case, this is the library that, for example, now I'm working on. It's under lab 10. If you just click on the PDF, I'm gonna post this in the also chat. So we have everything. All the labs are like in a single PDF. All right. So I'm gonna go back to my reservation, and it says here reservation scheduled. You should only see your reservation. So go ahead and click on enter lab. Right. So again, I'm gonna be splitting the screen into the content on the left-hand side and the lab on the right-hand side, which is under client. Okay. So I'll be skipping over the section 1, which is introduction. And here, because we're working with registers, reading, writing from registers, and hashing, so everything is explained here. For example, section 1, how do we read from registers? How do we write to registers? How do we compute the hashes? And so really everything you need is in section 1 in terms of the concept. And then moving to the next scenario. Okay. So step 1, we'll go ahead and open the topology. So click on mini edit, and the password is password. Now the topology for this lab is already built. All you have to do is load the topology by simply clicking on file open, and then here you'll see all the labs. In our case, it's lab number 10, and then select it. Okay, so once the topology is loaded, you go ahead and click on run. So now, once the emulation is running, these items here will be grayed out, and you can no longer manipulate the topology. So anytime you want to really manipulate the topology, add host devices, your emulation must be stopped. Okay. Now, let's see in the first step what happens if we ping from host H1 to H2, and because we haven't done any coding yet on the programmable switch, there should be no connectivity. So go ahead and click on hold the right click on host H1, choose terminal, and then ping 10.0.0.2. Here you see that there are like the destination host will not be reachable. And that's because the programmable switch is dropping all the packets. Right? Now, next in the section 3, we're gonna start programming the P4 program to calculate the inter-arrival time. To do that, we will first open load the environment, which is opening Visual Studio Code, where we write the code. So go back to the desktop. I will minimize this, and then open a new terminal. And here we're doing lab number 10, so we open Visual Studio Code with P4 Labs / lab 10. So code P4 Labs / lab 10. Okay. Once the Visual Studio Code is open, the first file that will be displayed is the headers.p4. So essentially what we're gonna be doing is we will define a custom header called inter-arrival time. And then in this custom header, it will contain a 48-bit value field called inter-arrival value. And why is it 48-bit? Because the time provided in the architecture is a 48-bit value. So under this command here, define the custom header below, write, define your header, enter arrival, and then bit 48, arrival value. Okay. Now, once you define your header here, you need to append it to the structure header. So in our case, because the inter-arrival header will be on top of IPv4, so I will just define it down here. It's of type inter-arrival _t, and then I will call it inter-arrival. Okay, so now our the header contains Ethernet, IPv4, and inter-arrival time. And just before moving to the ingress control, because we defined the header here, our parser already has a state to parse the inter-arrival time. So it's already implemented for you, but just to look at it, here we have after parsing the IPv4, if the protocol is custom of type inter-arrival, we just move here and extract the header. All right. Now, in section 3.3, what we're gonna be doing is that we will calculate the flows of the incoming packet using hashing, and then see where we can basically store it. So go to the ingress.p4 file here, and then first I will need to define a variable. I will call it flow ID. It's a 16-bit. Why? Because the hash output of the flow, let's say the 5 tuple, is a 16-bit value. It could be also 32, but we use the 16-bit. And to define the variable under the control block, just above the forward action, write bit 16 flow ID. Okay. Now next, I want to compute the flow of the flow hash of the incoming packet. To do that, I will define a new action and I will implement the hash algorithm inside this action. So again, I will define the action under the drop here. So I will call it compute flow ID. Yeah. So first, to define to compute the hash, you will write the term hash and then open brackets. What's good? The first input here is, or the parameter is the flow ID. So where do you want to store the output of the hash? I want to store it in the variable called flow ID, which I defined right here. Okay. And then next, you want to define the algorithm that you want. Connection available.
Now I can hear you back, Ali.
Sorry, there was no connection for a second. Okay, yeah. So next, I want to define the what hash algorithm I want to use. So in our case, we want to use the CRC16. So we'll just write hash algorithm dot CRC16. Then, so we also want to define what's the minimum output. So the minimum output is just 0. So you cast it bit 1. And then next, you need to define your fields. So on which fields you want to compute the hash. In our case, we just want to use the source and the destination IP addresses. So you can also define the port, protocol, and so on. So the first one is the header, IPv4, source address, and then comma. The second field is the source header, IPv4, and the destination address. Okay. And next, you want to define what's the maximum output. And the maximum output here is 65535, which is the number of entries in our register. So far I haven't defined my register, but I'm just defining the output of the hash, the maximum output of the hash. So it's bit 16. Okay. So with this action here, again, what I'm doing is I'm calculating the hash of the flow and I'm putting it in flow ID variable. I'm using the hash algorithm CRC16. This is the minimum output, and this is the maximum output. And these are the fields that I want to compute the hash on. Okay. So next, in section 3.4, I will be defining the register array, which will be used to store these interarrival times. So to define the register array, I will define it right below the flow ID. So the definitions are typically, for example, the register definition should be outside the apply block within the control block. How do you define a register? You write the keyword register, and then what are the fields that you want to store in? So in my case, it's a bit 48 because I want to store the timestamp. And then also you need to define the number of entries in the registers. So 35. And then finally the name of my register. So in my case, I will name it the last timestamp register because it will store the last timestamp, the last time of the packet that has arrived. Okay. Now let's also define another variable to store the inter-arrival time. So it's a bit 48, of course. I will call it inter-arrival value. Now, next, and step number 3, I will be defining an action, and what this action will do is as follow. So I will to calculate the inter-arrival time. First, I will read the timestamp from the register. So because the register will hold the last timestamp of the packet, I will read it, and then I will also get the current timestamp of the current packet, which is can be obtained from the intrinsic metadata, and then I will subtract them and save them in the inter-arrival variable that I've defined. Okay, so let's see how we're gonna be doing that. So under the compute flow ID, define another action. Call it get inter-arrival time. Okay. So first, let's define a variable called what's the last timestamp. Another one, the current timestamp. Okay. So where am I gonna get the last timestamp of the previous packet that I've seen? I will get it from the register. So last timestamp register dot read. This is how I will be reading from a register. We just read to execute the action read, and then you have to specify the index. Sorry, where you will be saving the value retrieved. So I will be saving it inside this variable called last timestamp, and then I need to specify which index, or basically the hash of the flow, which is bit 32, and it's saved in the flow ID. Okay. Now, for the current timestamp of the packet, this can be obtained from the intrinsic metadata. So current timestamp is gonna be, I need to access the standard metadata. It's called ingress global timestamp. If you're, so there are a lot of metadata that are available. It depends on the architecture. If you're curious about the metadata available in the V1 model, you just write for, and then if you go to the GitHub account, you will see these are all the intrinsic metadata available. So I think Ilya was talking about the queue depth, egress global timestamps, and so on. Okay. Now let's continue here. Because sometimes the packet could be the first packet arriving, so the last timestamp which is read from the register is typically 0. So let's take that into consideration by writing an if condition. If last timestamp does not equal to 0, so this is not the first packet corresponding to a flow, then the inter-arrival value is equal to the current timestamp minus last timestamp. Okay. Other than that, I will just put the inter-arrival time as 0. And finally, once we compute the enter arrival time, we need to update our register. So because the register holds the previous timestamp, now it needs to hold the current one. So how do you update a register? You write the name of the register and then write. You give it the index of the entry where you want to put your data, and it's bit 32, flow ID. And then what's the value that you want to update it with? It's called the current timestamp. Okay. So with that, I've defined my action that gets the last timestamp from the register, and then it's read from the register, it saves it in the last timestamp, and then it checks if this is the first packet or not. If this is not the first packet, then the enter arrival time would be the current timestamp minus the last timestamp. Otherwise, it's just 0. So finally, after writing these actions, again, they're not gonna be executed unless they were specified in the apply block. And so far, we haven't changed the apply block. It's just applies forwarding rule. What we need to do is now incorporate these actions and the logic inside the apply block. So scroll down. If the header of IPv4 is valid, then what's the first thing that we need to do? We need to check if the arriving packet has the enter arrival time header valid. So because we're not going to be computing the enter arrival time of any just like IPv4 packet. We have a custom packet that we're expecting here in the pre-for program that if that matches or if this is valid, then we compute it. So write if header dot enter arrival dot is valid. What you need to do is as follows. So first, I need to compute the flow, the hash of the flow of the packet by invoking the action compute flow ID. Next, I need to compute the enter arrival time by invoking the get enter arrival time action here, which does the registers. So get enter arrival time. And last, what we're gonna do is, because our enter arrival time value is now stored here in this variable, which is called enter arrival value, we need to update our header field with this value. So HDR, which is our header dot enter arrival value is equal to the variable enter arrival value that we define. Okay. So I'm just gonna be briefly repeating what I've done so far because this is the P4 our whole P4 program. It's not very complicated. So first, what we did is we have our headers. We defined a custom header called enter arrival time, a field that holds the time, which is a 48-bit fields, and we added to the headers. Additionally, we had our parser already implemented that takes that jumps into the state where it parses the enter arrival time. Now, next in the ingress control block, we typically had to do 3 things. The first one is to compute the flow ID. So the flow ID is here using the hash function, and we saved it in a variable called flow ID. The next thing is that we wanted to calculate the enter arrival time by reading it from a register using the flow ID index, and then subtracting it from the current one. The current one is obtained from the metadata. And last, update a register. And the third step is we simply need to update our header, the header of the packet that's incoming, with the inter-arrival time value. Right? So now let's move to part 4, which is basically testing our program. So first thing that I will be doing is I will compile my program. Hopefully I don't have any errors. Okay, so my program compiled successfully. Next, I will need to push the JSON output file, which contains the configuration of the file. I will need to push it to the switch S1. So push to switch basic.json and specify where you want to send it to. If it asks for a password, the password is password. All right. Now let's go back to mini edit right here and open a terminal on switch S1 by holding the right click, clicking on terminal. And then once you open a terminal here, let's verify that I have already have my basic.json file. Okay. Now, next, what I need to do is I will load the switch daemon, and I will need to specify the interfaces. So in our case here, we have interface S10, H1, ETH0, and ETH1. So I have 3 interfaces. So launch the daemon by writing simple switch, then -i, the first interface, S1, ETH0, then S1, ETH1, then 2. So 0, 1, 2 are just the logical numbers for the switch ports. Basic.json. Okay. So if the switch daemon is running, you should expect this output with then interfaces and their port numbers. Okay. Now let's load the entries in the table so that the forwarding is done properly. So for example, if the packet has a destination IP address host H1, we need to forward it here, host H2 there, and so on. So the rules are already written, so all you have to do is just load them in the switch by writing simple switch CLI and then give it the rules. Our rules in lab10/rule.cmd. And these are the rules forwarded. Okay. Now let's verify our program the inter-arrival time by sending packets, custom inter-arrival time packets from host H1 to H2 and host H3 to H4, and see how the receiver receives these packets. So first, open a terminal on host H2 by holding the right click on terminal, and then execute the Python script receive.py, and then we also need to add the option, the inter-arrival -p inter-arrival. So this allows the switch here to be aware of the custom inter-arrival time packet and display it properly. Now go back to host H1 here. It's already open. And now what I will be doing is that I will send packets to 10.0.0.2, which is host 2, H2. And then I will be sending 10 packets per second. So you specify the option 10. And then what's the type of the packet? It's an inter-arrival time packet. Okay, so go back to host H1 and observe what's happening. So now host H1 is sending packets to host H2 10 packets per second. What's happening is that on host H2, it's displaying the received packets over here, and you see the first Ethernet, then you have the IP, then on top of the IP you have the inter-arrival time, and it's as you see here, it's showing a value 100,000 microseconds, 100 microseconds, which is 100 milliseconds or 10 packets per second. Okay. Now, so this is with 10 packets per second. So let's see if we send 20 packets per second, and this time it's gonna be from host H3 to H4. Okay. So on host H4, hold the right, open the terminal, hold the right click, and then receive .py -p enter arrival. So just a quick note, this receive.py and send.py are all custom, we developed them in our lab. If you're really interested on seeing how you can send a packet and what's going on, all you have to do is, let's say you wanna see the receive.py, go to user bin receive.py, and then you can see all the options, how is the packet received, sent, and so on. Okay. Anyways, let's execute the receive.py enter arrival. Okay. So now I will go back to I will go to host H3, open a terminal, and now I will be sending packets to host H4 10.0.0.4. I will be sending it 20 packets per second, so the argument 20, and they're all of type enter arrival. Okay, so let's go back to host H4. Here, what you will see is that there are 50 packets per second or 50 milliseconds, but here it's displayed in microseconds because that's how granular P4 is. All right, and you can see the difference between receiving on host H4, which is 50 milliseconds, and receiving on host H2. Let me show them next to each other. So here this is 50 milliseconds, and here this is 100 milliseconds. Right? So with that concludes lab number 10. Let me know if you have any question or any comment. Just feel free to type it on the chat or unmute yourself. Thank you.
Thank you, Ali. I don't see any questions, but this is for you or Eli or Ali Maslum or Jose. Do you wanna briefly show an application of packet inter-arrival time? What can we do with that? I don't know if
Yeah.
Mm-hmm.
So I can talk about my research. So like I use the inter-arrival time to calculate the inter-arrival time between DNS, let's say responses or requests, and I use this inter-arrival time to as a kind of a feature among other features to identify malware or benign traffic. It's a very powerful feature because really for example, in terms of malware and benign traffic, there could be a significant difference in the rate that they're sending data. Can you hear me?
I think we lost you for a few seconds.
Oh, sorry. I can repeat the last part. I was saying, when you're like, for example, working in cybersecurity, there's a difference between the traffic in benign host and malware. So inter-arrival time could be a very powerful feature to see how the packets are arriving. So I use that.
So what you are suggesting is that malware generated flows tend to have certain packet inter-arrival times that is different than regular traffic.
Yeah.
All right. Italo, it says, Ali, could you please point out for publications you might have on these subjects? Ali, I don't know if you want to share, or I know that we have the slides online, but you want to very quickly in 5 minutes talk about any publication related to packet inter-arrival times, or I can do that too. Let me do it, Ali, 1 minute, and then you will get ready. I'm sure that you have much more than I have in mind right now.
Okay.
So Italo, one application that we did recently in packet inter-arrival times is, I will go to the title. This has been published very recently. Is the detection of blockage in millimeter wave networks. So millimeter wave networks are wireless networks where the links are very directional. It's millimeter. And one way to quickly detect when there is a blockage and then adjust or basically switch from one station to another when there is a blockage is to detect this blockage in the data plane. For example, here we have a scenario. The y-axis is inter-arrival time in milliseconds, and the x-axis is time in seconds. And suddenly, between 5 and 10 seconds, there is a blockage. I believe the blockage is at time equal to 6. And you can see that in the data plane, we can very quickly detect that something was disrupted. I mean, the connection was disrupted. So the idea that we use at USC is that if there is a user that is using this technology, millimeter wave, and we tested this, and there is a disruption between the user and the access point, we can very quickly detect. I mean, we're assuming that all the traffic is going through a switch. This is the infrastructure network, they switch, and then to the base station. Once we detect this blockage, we can quickly switch to an alternative path, an alternative access point. And we found, I mean, this is the measurement in the lab. We see that Ali is being between the phone that is there and the access point, that is the red line. And the approach improved quite a bit compared with state-of-the-art work and 802.11 that use this millimeter wave technology. For example, the top is the proposed system, and then the bottom is current systems that are in the market. And we can see how throughput is about 1 gigabit per second, a little bit slow, slightly of 1 gig, but how our system recovered pretty quickly. The secret here is that we have much more visibility in the data plane. For this example, we use inter-arrival time, packet inter-arrival time, to detect that there is a disruption in the system. So I hope that give you an example of inter-arrival time, but now I will let Eli, if you have anything, Eli, to add, or any other application you might have in mind.
Yeah, I mean, I think like using those are like inter-arrival time is really effective, even for like classification of flows. Like if you have encrypted traffic and you have a bunch of traffic coming to your network, you can basically model how your typical, let's say, voice over IP look, because, you know, with some codecs, packets might be separated with a specific amount of time, like 20 milliseconds, for example. So you can basically identify traffic. There are some applications on that. There are others on heavy hitter detection. So based on the interarrival time, also you find a distribution, and then you can see if a packet is generating a large amount of traffic in a short period of time. Another one is for congestion control and TCP, what Neil was talking about in the morning. With congestion control like BBR, for example, they do pacing. So they set the rate, and then TCP would start sending kind of in an evenly spaced manner. So the time between the packet is more even than when you look at congestion control like Cubic or Reno. So even those can be, I mean, very useful for if you are trying to identify the algorithm or understand its behavior. And as Ali was saying, there's a lot of applications in security as well. They use them as features in some machine learning algorithm. Also microburst, if you compute the interarrival time between like consecutive packets belonging to a flow, you can identify microburst. I think, yeah, these are, I mean, what can pop on my mind. I can compile a list of publications and send you.
Thank you for the question, Italo. Right, I don't see any new questions. I will go to our workshop website. And again, we'll be posting the recording of today at the bottom. And all the material is there. And we want to ask you, we just sent an email, if you can provide some feedback in the form of a survey that you should have received a few minutes ago. With that, we're concluding this workshop. I don't know if Marian, you are the co-organizer. Are you there? You want to have a few last words? Marian is not there. So this is concluding our workshop. I want to thank you all for attending. Any feedback is welcome. And if you are interested in any of these materials, including accessing our lab libraries, just let us know, send us an email, and we give you access to all this material. So thank you very much. Have a good rest of the day.